So I guess there is a microphone up here, so I can sort of hear it being mic'd. So good morning. I'm Steve Schwartz. Georgia and Anu asked me to give a few welcome remarks. So thank you all for coming today, and I guess there'll be some more people coming in after rounds and the units finish. Georgia and Anu and Cecilia, Alex, Gail have prepared an excellent day, a mix of talks, both about the past, the present, the future, as well as some practical stations that I think you'll find interesting, a good mix of, again, standard things, some sort of new and out there things in terms of learning about cardiac anatomy, and I think it will be a terrific day. I don't want to cut into everybody else's time. Did you want to do some housekeeping things? So enjoy the day. I hope you get a lot out of it. Thank you to all the people who've volunteered to talk and to proctor sessions, and enjoy.
Thank you, Steve, for that welcome address, and welcome everyone. My name is Anu, and on behalf of the practical team, I'd just like to take a couple of minutes to go through the running order of today. You'll find on your tables the day's agenda. The morning session consists of 3 excellent talks. At the end of each talk, we will have time for audience participation with questions, and we encourage your active participation in these. For the speakers, there will be a 5-minute and 1-minute warning before the end of your speech. Please pay attention to these so that we have time at the end for questions. We also ask that the speakers use the microphone provided so that our friends overseas or those who are joining us via webcast can make the most of the session. The mobile interactive stations are going to be happening in the gallery, which is situated outside and to the left of this room. We will divide you into 4 groups and give you a briefing before this session so you know what to expect and how to make the most of these sessions. Tea breaks and lunch will be served outside this room, and we will commence the afternoon session promptly at 1:30 back in this room. The format of the afternoon session is similar to the morning session with 3 fantastic talks, and we will conclude with a stimulating panel discussion on challenging cases. I am not a Twitter user. If you are, however, a Twitter user, then please follow the Twitter handle. I hope I'm using the terms correctly. That's the hashtag. We encourage you to follow via Twitter if you are. Please feel free to approach myself or others in the team, Georgia, Alex, Gail, and Cecilia, if you need any assistance or have any questions throughout the day. We hope you find the day useful and interesting, and on behalf of the team, thank you so much for coming. And to those of you viewing via webcast, thank you so much for joining as well. That's it.
Well, I have the privilege of introducing my former teacher, continual teacher. It's a huge biography here, Des. It's going to take more than the time it's going to take you for the talk. I might forego it all. No, just kidding. So Des, when I was a fellow here in 94, 95, was one of my teachers. Tough guy to really get someone to recognize that you're suddenly clinically ready. But when you are, man, he's great. And expectation is high excellence of clinical skills, and the expectation is that you always do the right thing. And those are the things that I learned from him over the time that he was here, both as one of the associate staff and then ultimately taking control of the unit for a while in the department. He decided to retire, which was crazy in 2011, but he's not really retired. Just want to let you all know that. He continues to be a very integral part of our critical care transport pediatric team across the province, and also part of the coroner's review for those patients. So I want to welcome Des up here to talk to us a little bit, maybe a lot, about our history with cardiovascular and how we've come forward. Thanks, Des.
Thanks so much, Gail, and good morning, everyone. It's always a great pleasure to come back to Sick Kids, even though at this stage of my career it's to talk about historical perspectives. But I find history fascinating, and I think at the end of this talk you will be quite amazed with some of the things that happened like 20, 50, almost sometimes 100 years ago. So this is a brief history of cardiocirculatory support as it pertains to congenital heart disease. And so let's start here with one of the great advances in the 1950s. So up until this point, operating on the human heart was impossible. You can go back to 1937, 1938, when Robert Gross in Boston was the first person to do a ductus ligation, and then he did coarctation repair. But to actually operate on the heart was almost impossible because the organ is beating. You can't stop the circulation without affecting blood flow to the brain. So it was sort of unknown territory. But this is Bill Bigelow. Bill Bigelow was a thoracic surgeon at Toronto General Hospital, and he started doing some experiments on using hypothermia to protect the brain in the situation of circulatory rest. And this is a very crude apparatus, I suppose, by our lights nowadays, but you see here somewhere in there there's a dog, and the dog was cooled down, and then ventricular fibrillation was induced. It was cooled to less than 30 degrees Celsius. And for a period of 10, 15 minutes, there was no circulation, no CPR, no blood flow essentially. And then they would defibrillate the heart, warm the dog up to normal temperature, and then look at what they had. And to their gratification, they found that the dog performed normal doggy things after this experimental procedure. So now they had a window whereby they could start thinking about bringing this into the human sphere and perhaps introducing it into the repair of congenital heart disease. Now, in those days, there was no valve replacement, there was no coronary artery bypass grafting. It was all about surgery for congenital heart disease. And so what they did was, and this is the original report in the Annals of Surgery showing that no cardiac output for a period of 10, 15 minutes with an intact animal at the end of the procedure. So they introduced this into the sphere of cardiac surgery. And this is for the repair of simple congenital heart defects. We're talking about ASDs, not VSDs, not tetralogies, but simple ASDs where you could do the procedure with a slick surgeon in 10 to 15 minutes. So what they did was they anesthetized the patients, and this is a sort of an example of what was going on at the time. Anesthetize them, put them into this ice bath here, bring the temperature down to less than 30 degrees Celsius, and then it was inflow occlusion. So they'd open the sternum, they'd put a ligature on the IVC, ligature on the SVC, interrupt the circulation, fibrillate the heart, and then the surgeon had 10, maybe 15 minutes at the broadest in terms of repairing the defect, and then when that had been successfully accomplished, you had to de-air the heart, and then close the heart, and then release the ligatures, defibrillate, and warm the patient up. And this proved to be pretty satisfactory as long as you had a speedy surgeon that could get the procedure done in that period of time. But you were limited to about 15 minutes at the maximum, because obviously the longer you go, even in the presence of hypothermia, the more ischemic brain injury you're going to get. And this is very typical, an example of case reports of the time, closure of an ASD with hypothermic arrest. Again, the example of the bath here, patient cooled to 28 degrees Celsius, inflow occlusion for 5.5 minutes, and a successful repair. So a pretty significant advance, but it was limited obviously to repair of simple defects. The next big advance was the development of a cardiopulmonary bypass machine. And this is John Gibbon, and that's actually his wife here, who is his collaborator. And this is their heart-lung machine here. Fairly substantial piece of machinery by our lights nowadays. But they developed this machine to support the circulation for the use in cardiac surgery. And this is the graphic representation of the first successful repair of an ASD in an adult female, May 1953, using the pump oxygenator developed by Gibbon. And this was, again, a landmark in congenital heart disease surgery. Now, you'd think, well, fantastic, a new frontier has been broken through, and this would be adopted across the world, and this would become the standard for open heart surgery. But no, that was not the fact, because this was a very crude device, and I think a lot of surgeons felt that using this device with a lot of complications was more risky to the patient than doing the inflow occlusion with hypothermic arrest. So it didn't exactly catch on in the cardiac surgery world. Now, I've shown you Bill Bigelow before, and this is another giant of the time, also a Canadian. This is Bill Mustard. And Bill Mustard worked at Sick Kids. He was originally trained as an orthopedic surgeon. A lot of experience during the Second World War, operating on battlefield casualties. And in those days, if you were a surgeon at Sick Kids, you did a bit of everything. You did a bit of orthopedics, you did a bit of thoracic, you did a bit of abdominal surgery. You were a jack of all trades. But eventually, the head of surgery at Sick Kids told him that he had to focus on one. He could do heart surgery or he could do orthopedics. So he elected to do heart surgery. And this is, again, a landmark event in the annals of congenital heart surgery. And this is the atrial repair for transposition. Now, most of you in this audience have never seen a Mustard operation. But this was a huge breakthrough, because you're taking essentially, at that time, a critically ill infant, severely hypoxemic, for which there was no surgical remedy. So he developed what was the atrial repair for transposition. And essentially what it was, first of all, the patient had a Blalock-Hanlon procedure done, and then they would have a baffle placed in the atrium here, which baffled the deoxygenated blood into the morphological ventricle here, which supported the pulmonary artery, and then the morphological left ventricle, or the systemic ventricle, pumped oxygenated blood to the circulation. Now, this was a huge breakthrough at the time, because for babies born with this condition, there was no remedy. But this became the standard procedure, and this was published in 1964, became the standard operation for transposition of the great arteries. And at Sick Kids, from 1964 up until about 1980, they did hundreds of transpositions with the atrial switch, with a mortality of around less than 2%. So it was an enormously successful, short-term successful operation, because obviously the long-term effects were not good, because you're asking a ventricle that was not designed to support a systemic circulation to be the main pumping ventricle. And the long-term results was that this ventricle would fail eventually. So it then became superseded by the arterial switch operation. But, and this is the sort of thing you think, they did what? So Mustard felt that the cardiopulmonary bypass machine that was invented by Gibbon was too risky, so he developed his own cardiopulmonary bypass machine, and this was a picture of it, and he used monkey lungs in series as his oxygenator device with a crude pump here. Now, the story goes he did 5 of these in a row and they all died. And then he persisted and the 6th survived. Now, you can imagine if this happened today, would he be allowed to operate on 5 using this crude device here? I mean, the surgeon-in-chief probably would have stopped him after he'd done the first one. Different times, different standards. But it was a breakthrough, and Mustard was an amazing character. He's one of these larger-than-life characters. He posed for this photograph here, and it was meant to be a sort of, Time magazine Man of the Year type photograph. And here he is posing with the model of the heart here. And he was an amazing showman. He was the most significant self-publicist I ever met. He was just actually ending his career in 1975 when I came to Sick Kids as a fellow. But that was a very significant breakthrough. But for other congenital heart defects, like things like tetralogy and for VSDs, that, the gibbon oxygenator had not caught on. And they did crazy things like cross circulation. So this is the cardiac pulmonary support was provided by one normal person, and the patient being operated on, the support for their circulation came from this cross-circulation device here. This is Walt Lillehei, who was one of the pioneers of congenital heart surgery. It's the only operation with a potential 200% mortality. But it was amazingly successful. They reported this in 1955. They had no mortality in the donor circulation, and a very respectable long-term survival in the patients who were operated on. So you can't even countenance doing something like this today. The next big step forward was the development of this bubble oxygenator, and this is, again, Lillehei and Duvall from the University of Minnesota. And this is their device here. This is essentially a big plastic bag here where you bubbled oxygen through blood here, and oxygenated blood, and then it had a pump that returned it to the body. Now, this was fine for short-term open heart surgery. It was a very efficient oxygenator, but for long-term support, it didn't work really well because you got a lot of hemolysis, you got a lot of destruction of platelets and white cells. So to think of doing it for more than a short-term open heart surgery was not ever contemplated. But from the 1950s up until the late 1970s, this was the standard oxygenator used in the cardiac operating room for open heart surgery. People weren't really countenancing in those days of taking this technology out of the operating room and bringing it to the ICU, but there were some tentative attempts to do this, and this is an example of a case report. This is a baby who had transposition, who had an unsuccessful operation, so they devised this sort of very crude pump and oxygenator and rewarming device here for short-term support. I mean, the baby died, but technically it seemed to be effective. So they got a case report published in the Annals of Thoracic Surgery. But people were beginning in 1970 and in the late 1970s to think about taking cardiopulmonary bypass technology out of the operating room and perhaps bringing it to the ICU. And the landmark event in this was, first of all, the development of the membrane oxygenator, which was much more efficient for gas exchange, much better for long-term support because you got over a lot of the problems with hemolysis and destruction of red cells. And this is the first case report of taking this technology out of the cardiac operating room and bringing it to the ICU. This is published in the New England Journal because if you do a landmark case report, then you get it published in a high-ranked journal. This is the membrane oxygenator, which is developed by Ted Kolobau. It was a huge device. You would, compared with what we use nowadays, it was an immense device. And you can see here surrounding, and this patient was a traumatic pulmonary injury with ARDS, and they supported her as an adult and supported her in the ICU for a period of days, successfully decannulated, and the patient left the ICU, so they got a case report in the New England Journal. So this is the first example of long-term pulmonary support using extracorporeal technology. Now, when you develop new technology, you get people use it, they publish case reports if they're successful, but at some stage you've got to produce something more convincing to get this device generally accepted. and this was the randomized trial of ECMO support for adult ARDS, published in JAMA in 1979. This was funded by the NIH because they wanted to see whether it was better than conventional therapy. And among the authors here is a name that's familiar to us, and certainly to Gail and myself, and this is Bob Bartlett. I'll talk more about Bob Bartlett in a minute because he is one of the most outstanding individuals I think that either of us have worked with. So it's a randomized, prospective randomized trial. Now, what I'm going to show you on the next slide, you'll probably throw up your hands with horror and say, how could they even design a trial like this? So they designed a trial which had a total of 75 patients. The standard therapy, mechanical ventilation, or the control arm, consisted of positive pressure ventilation with 5 centimeters of end expiratory pressure. You think, what, 5? Are they crazy? But at those times, there were big debates about whether 5 or 6 or 7 would adversely affect cardiac function. So people were very cautious about adding PEEP. So in the control arm, just shows you how things were in the 1970s. The overall mortality in the study was 90%. All the patients died. And in the ECMO with therapy arm, the mortality was no different to those in the control arm. So what happened then is people said, oh, ECMO, it's no use, forget about it. NIH withdrew their support, and it sort of died a death. Well, not quite, because of this man. This is Bob Bartlett. Gail knows him extremely well because she worked with him for many years in Ann Arbor, and he's the father or grandfather of ECMO therapy. And at the time when they did the adult study, he was working in California. He moved to University of Michigan at Ann Arbor, and he pioneered this technology for the use of neonates with acute hypoxic respiratory failure. So these were typically patients with meconium aspiration syndrome, PPHN, who were dying of hypoxemia. And their circuit, which would be very different to the one we use now, they used a roller pump, they used obviously a membrane oxygenator, heat exchanger. The cannulation technique was the SVC and the innominate artery down to the aorta. You're all aware of this stuff here. But he, then at the University of Michigan, pioneered this device and continued to propagate it as a way of supporting neonates with acute hypoxic respiratory failure with an overall survival of around 80%. Now, all this, if you go to the ELSO registry, you'll find that, how many get, there's maybe 40,000 now, Gail, is there? 40,000 neonates supported with ECMO with an overall survival. So he started something which essentially really took over the treatment of neonates with acute hypoxic respiratory failure and started thinking about maybe if it works for pulmonary failure, it's the same technology, why would we not think about using it for cardiac support? Now things have changed. So they used to use a roller pump, which now is sort of obsolete technology for support outside the operating room, still used in the operating room. And we're now using something like a constrained vortex or this pump head here, which is a much simpler device, which has less complications. And pump technology has come on in leaps and bounds. I think you're all familiar with this pump device, which is the one that's commonly used now for either cardiac or pulmonary support. It's a very compact system. It can be deployed and primed and deployed in a very rapid sequence and brought to the bedside to rescue patients with either cardiac or pulmonary failure. That's not the only device available. This is a Levtronic, which is again a very simple, a very simple compact cardiac support device. And of course, membrane technology has come on in leaps and bounds. If you compare the membrane lung used here in 1970 with the new membrane lungs here, they're much more compact, they're much more efficient, and they allow for much longer support without the development of adverse events. So it was obviously a matter of time before it was to be deployed for use in the ICU, and this is one of the first case series of extracorporeal membrane oxygenator rescue therapy for children after open heart surgery, or ECPR as it has now become known. This is Pedro Del Nido from Boston and Ann Thompson from Pittsburgh, Heidi Dalton from Washington. and they put together an 11-case review of eCPR deployed in the post-operative period to rescue patients who had cardiac arrest, 11 cases with 7 survivors. And we, together with other colleagues in Boston, put together this case series of use of ECMO or 12 ECMOs on 3 VADs for patients with acute fulminating myocarditis. And these are sort of extraordinary results where you've got patients children who develop acute myocarditis, develop catastrophic heart failure to the point of cardiac arrest, emergency deployment of ECMO cannulation with support. And in this case series of 15 patients, there was a return to normal cardiac function without transplantation. So this is a primary therapy with an overall very good non-transplanted survival. So again, this opens new vistas of support for patients with severe heart disease. And I think we're all familiar with the Berlin heart now, which is the technique that we deploy primarily for patients who are going to be need long-term cardiac support for either myocarditis or cardiomyopathy. So it's always good to end on an anecdote. So, and this is one of the cases that really caught the imagination at Sick Kids. And this is a young lady called Heather. And Heather was from Dundee in Scotland. And she was 16 years of age when she came to Sick Kids. And she was coming from Dundee to Ohio to take part in a bagpipe competition. And on the flight over across the Atlantic, she became acutely ill, was taken off the plane at Pearson Airport, taken to the local hospital in Etobicoke, where she was in catastrophic heart failure. She was severely hypertensive on massive doses of inotropes and looked like she was going to die. She was 16 years of age, so she was transferred to Sick Kids. The interesting part of this story was if she was 18 years of age or older, she would have died because there was no hospital in Ontario that was offering cardiac support outside the operating room for patients with catastrophic heart failure. So Heather arrived directly into the ICU, and it was obvious she was going to die. So, and this was the mid-1990s, and our ECMO program had just sort of taken wing. So we decided that she definitely qualified for ECMO. We weren't sure what the etiology was, but she needed to go on ECMO or she was going to die. So she had an emergency cannulation, put on ECMO support, stayed in the ICU for probably, I think maybe 4 weeks or even longer, a long recovery, return of cardiac function, but a lot of multi-organ dysfunction. And at the end of the day, survived. And this is her on her 18th birthday. We stayed in touch with Heather. The other interesting part of the story was her parents had never been outside Scotland in their lives. They didn't even have a passport, so they had to go to London to get an emergency passport to come over here. Her father worked for the post office in Scotland, and he's used to deliver mail, so he used to walk around the hospital because that was his way of relieving stress. But and this is a cutting from the local Dundee Chronicle that Heather sent us some years later. Here's a picture of her in the ICU. They wrote up this story about Heather and her miraculous recovery at Sick Kids. Mother's Pride is a type of bread that's sold across the country in the UK. So, and she's referred to as Mother's Pride throughout the article. I'm sure they got a little boost from the people who made Mother's Pride to put that in. But it was a fantastic story, and and there were a lot of skeptics at the time. What are you doing with all this extracorporeal technology? Because some patients didn't do well. So, people always question new innovative technology, and it's invasive, it's expensive. Some of the results are not as good as one hoped, but this was a key in getting this therapy established in ICUs in Sick Kids. And it's a great story because she subsequently married and she has kids, and she keeps in touch with us from time to time. But that was Heather's story. And with Heather's story, I leave you with a sort of a very broad perspective of how cardiocirculatory support has been developed over 100 years, from the beginnings of open heart surgery in North America to the advanced technology we use in the ICU today. So thank you very much for your attention.
People have to have questions. Any questions? Oh, good. We have a few. That's good.
Thank you so much, and thank you so much for being part of our day. We're really, really having your reputation precedes you. I'm going to ask you a bit of an unusual question.
Yep.
If tomorrow morning you could wake up and telephone your 25-year-old self and give yourself career advice or do something differently, what would you say to your 25-year-old self?
I would say that it's a very good question. So I would say to myself, I'm glad I worked in ICU at the time that I did, because like the advances we saw in intensive care medicine from when I was a fellow here in 1975 to today have been spectacular. And I always use the analogy of the low-hanging fruit. So when I was a fellow, what kept us up at night? What were the things we worried about? What were the things that we found most challenging? Things probably you've never even seen. Acute epiglottitis. Right? You've probably never seen a case of acute epiglottitis. That was something that was, very challenging. A patient who was in acute danger of dying, but a simple procedure, putting a tube in the airway, it was something that was, quite frightening to do because you couldn't see much, but you knew once that tube was in the airway and 2 doses of antibiotics, that child would leave the ICU and never come back to the ICU ever again, hopefully, because it was a one-off, very easily cured problem. So that's an example of the very gratifying results that we would see at that time. Things that used to concern us, like in open heart surgery, things that were challenging in our day were a Fontan operation. You think, oh my God, a Fontan operation, like this is going to be like days in the ICU, and now it's like they're out the next day, and of course that's all about case selection and doing a staged reconstruction. So what I'm trying to say is I'm glad that my career spanned that time when problems were more simple, remedies were were easier to come by because the problems themselves were simple. So now I think of what's happening now, and I think the problems are much more challenging. The patients, the families are much more challenging. They've all been on the internet. They all know this is that and sick kids is like, where miracles happen. I think there's a downside to promulgating that, because if the miracle doesn't happen, the parents don't want to know why. And if you talk about ECMO and cardiocirculatory support, we're in an era where we're using it like so often, and a lot of the results aren't good not because we're not able to do the technology. We're experts at the technology, but when you get a patient on the ward as an arrest, there's an automatic sort of prompt to deploy ECMO to rescue the patient, and those results are not all they're cracked up to be. And it's when we started doing ECMO for pulmonary support, the cardiac surgeons weren't really interested. They didn't. They felt that it was, they'd done the operation, and there was, they'd be wasting our time by putting them on ECMO in the ICU. And it's moved from that to, when I left the ICU, the most common use for ECMO was after cardiac surgery. And, you've got to be sure that you're not using ECMO after open heart surgery because technically the operation has not been successful because there's a residual defect that's been not noticed or underestimated. So, my concern nowadays is that we're using it too much, and some of these cardiac supports are going on long, for long periods of time, when sometimes it's fairly obvious that they're not going to be successful. And it's difficult to back away from that because once you're in, right? So for that reason, I'm very happy to say that my career spanned a time when the problems were less challenging. They were exciting times because, we had relatively maybe simple problems that we had solutions for. Things like Reye's syndrome. You've probably never seen a case of Reye's syndrome. That was like some of those adolescents. They were critically ill. They were probably going to die, and we would rescue them. We'd even, the surgeons would decompress the cranium and open the brain up, and with some astoundingly good results. Not all good, and again, that's an example of a disease for which we had a remedy with some good results. And I feel we're now that sort of window is shrinking down to the very challenging cases where the remedies are available, but the results are not as good. So I'm glad I worked when I worked. I would not perhaps be as enthusiastic about starting now.
So now we're going to have to bring our trainees off the walls. But Des, just great, fantastic talk. And just to build on that and some of the things that you mentioned, looking at the future, it's always good to look at the past. And as you go through, where do you see the ICU going? And how can we get there if doing research and being innovative to the degree that people were before us is challenging?
Yeah, it is, because in terms of innovative stuff, it was much easier in those days. Like when I started working with high-frequency oscillation, we did dogs and pigs in the lab, proved that it worked. It was a very effective gas exchanger, and we didn't do any clinical trials. We took the machine, sort of wiped it off, got rid of the dog hair and stuff like that, and brought it to the ICU. And the first people that were oscillated were Charlie Bryan and his wife. That they volunteered to sort of be intubated, and you wouldn't get away with any of that stuff nowadays. So, I mean, it sort of has made the innovation more challenging, I think. And because everyone wants, if you think of a new idea or you want to try a new therapy, people want you to do a randomized controlled trial. And it's like, not everything in intensive care medicine lends itself to a randomized controlled trial. In fact, I think there are very few things that lend themselves to randomized controlled trials. So I think, we've gone a bit too far in the evidence-based medicine approach because, things like ARDS, it's a heterogeneous disease. Like it's not a disease, it's a syndrome. And they have more than just pulmonary failure. So I think it's, trying to do innovative stuff now is more challenging than it used to be. I think we've perhaps reached a time when the gains are going to be less spectacular. Like, brain stuff. When I was working as a fellow, we were all excited about using hypothermia based on what cardiac surgery had shown. We could use cool patients down after head injury, cool patients down after hypoxic ischemic brain injury. There were no trials done. We just took what was shown in the animal lab, took what was shown in open heart surgery, and say, it must be good. Let's cool these patients down. So we cooled all these patients down. No, it wasn't good. And I think we've reached a sort of trying to make progress in brain injury in intensive care medicine. I think that's one of the frontiers we haven't really breached.
We are, unless it's a 30-second question.
I can get him to answer it with one answer. One word answer.
Okay.
After repeated failures, people still kind of persisted with these things, with many things, not just devices and whatnot. Do you think it was ego or maybe a sense of that this was going to work that made them persist?
Yeah, I think it was it was probably a sense of this is going to work. Like I quoted you examples of animal studies. If it works in an animal, and these weren't mice, they were dogs and pigs. It's got to work in humans, and you don't have to do a sort of a big case series. Let's go jump straight from the bench right to the bedside, and that was one of the problems with HFOV, that the initial high frequency trials in neonates, like they were, that they went straight from the bench to the bedside, and they were poorly designed, and people didn't understand what they were doing properly. So I think it's trying to make that leap too quickly. Perhaps gets us undone.
Thanks, Des.
Thanks for having me, first of all. And I'm going to speak about regenerative medicine. And I know regenerative medicine isn't really new to the cardiovascular field, but it's pretty striking looking into literature how rarely it's been applied in congenital heart disease. So I'm going to highlight a few aspects that are potentially important for us. And I'm probably raising more questions than bringing up answers. So this is basically hot off the press. It's the 6-year results of the single ventricle trial, just recently published in Circulation. And some of you may say, well, he was supposed to speak about like new things, about innovative things, but we've seen these curves and they don't look any different. But that's exactly where I'm going. So single ventricle trial has been comparing RVPA shunts with MVT shunts. And the results still, long-term results, somewhere in the 60% range. And while we can say, well, we've done pretty well, and that's how all these papers start, claiming how we've improved over time. It's not only that we are still at 60%, it's also that hypoplastic left heart syndrome is by now the largest cost factor in pediatric cardiology. It ranks 7th amongst every kind of pediatric diagnosis, and that's with about 1/3 of the admissions compared to other diagnoses that are high up in the ranking. We're better, but that also means that patients are reaching adulthood more easily, and that we're all expected to see the number of adults with hypoplastic left heart syndrome to double in the next few years. And about 40% of the costs that we spend on all these patients, they occur after palliation. So from that perspective, looking at the long-term outcome, once they've reached Fontan, they do quite well. But all those that are failing, like 61% of them, show ventricular dysfunction. And there is no proper treatment, especially nothing that is specifically tailored for either hypoplastic left heart syndrome or other kind of patients with single ventricle diseases or any kind of right ventricular failure, for example. And it's too easy to say we just apply the established heart failure treatments that we have in adults. The right ventricle, even though there aren't too many studies that actually have shown that there is a significant difference between RV and systemic LV in the outcome in the end, the RV isn't an LV. It's physiologically different. If you look at the pressure volume curve, it's very different from that we see in the LV. It's genetically different, even though we have still not yet completely understood how RV and LV developed from a fetal perspective. And it's, from its morphology and from its structure, different to the LV. And we see right heart failure, as I initially said, not only in single ventricle patients, we see it with a lot of adults, especially across the street with long-standing ASDs and VSDs. We see it as a consequence of tetralogy of Fallot. And all these patients are usually expected to have a very good long-term outcome. We see it obviously in the single ventricle population, and we see it in patients with pulmonary hypertension. There is an initial episode where they adapt quite well with some kind of adaptive hypertrophy, but it switches during failure to maladaptive hypertrophy, and that is not reversible. But we have another benefit in our patient population, and that's that we have young patients and we can treat them early. And the growth potential can be quite significant. Like you may say, well, 0.01% or 0.02% cardiomyocyte events in a growing myocardium, that's not really much, but it's more than what we see in adults. Like studies have shown that once they reach 20 years or older, there's rarely any cardiomyocyte differentiation anymore. And we can exploit that potential eventually. There has been one trial, and I'm sorry for the graphics because that's a little bit distorted based on that it's not run from my own laptop. There is one trial that has tried to use the regenerative potential, and that's from the Japanese group that has used cardiosphere-derived cells and injected them either before stage 2 or before stage 3. And they've shown that especially those with reduced ejection fraction, they benefit from the stem cell treatment. They've also seen that it's not only a benefit in survival, but also, and again, excuse for the curves here, they also see a benefit in freedom from late failure in those who started with the reduced ejection fraction. But cell delivery itself is difficult because cell engraftment has been shown to be pretty limited in these patients. So this study that I'm showing, and it messes up my graphics here a little, this study has actually shown that in a primate model, there is initially quite good engraftment, and 0.4%, that's just generally speaking, good engraftment in cell delivery. But during follow-up at 140 days, there were basically no cells detected anymore. And still, the primates showed an improved function based on the cell delivery. So we have to question whether it's cells that we should deliver or whether it should be something else that is probably secreted by the cells. That's another histology example where there are basically no cells found afterwards. And other groups have shown these results quite strikingly, that the red group here are those that, it's a murine model basically, where cells were delivered versus those that basically just received the secretome. So the secretome is everything the cells secrete into culture medium. It's not cells, it's any kind of miRNA, it could be factors itself, it could be any kind of vesicles that they secrete. And they've shown that not only they have the same, but they have better mechanism than cells themselves. We've looked into tissue cultures derived from both an LV in hypoplastic left heart syndrome and an RV in hypoplastic left heart syndrome, and have also seen that the cells that you get from each of these ventricles are very different. So those of the LV, even though it's hypoplastic, they have more differentiation capacity than cells from the right ventricle. So we are approaching this from a multi-institutional approach, basically using everything that we have good access to. We use people at the University of Toronto, especially from TBEP, where they do bioengineering and look into nano packaging. We look into the biobank and the VAT program at the Toronto General, where they have a multitude of tissue samples from heart failure patients. And we work together, and that's where I'm the PhD student at, work together with a group at the McEwen Center that are looking into basically induced pluripotent stem cell research. And what we do is not only assess how cells engraft in different types of cardiac defects, but also we look into what kind of secretomes we see and in which way these secretomes differ. Overall, we try to, first of all, get a good understanding of like what the true mechanisms of these cells are. Like there's, I would say, a tendency that cells basically elicit their effect not by cell engraftment, but by the factors they secrete. And by using mass spectrometry, protein microarrays, and mRNA analysis, we try to narrow this down to not only a very broad, undefined soup, so to say, that is given to the heart, but to a few factors that can basically create the same effect. We're going to look at the function and the effects on angiogenesis and senescence in basically tissue culture, and we also want to do in vivo studies in murine and in pig models to better understand which of these factors are potential therapeutic targets. But there are obviously a lot of limitations. First of all, pressure overload, which is commonly called as one cause of RV failure, it's not all, like not every pressure overload is the same kind of pressure overload. So what we know from animal models, for example, is that pulmonary artery bending, that's pretty well tolerated by the RV, and it's pretty difficult in the long run to cause the RV to fail just by bending the pulmonary artery. Pulmonary hypertension models, they may stress the RV a little bit more and cause quite reliably the RV to fail, but it's not really the same type of failure that we expect in hypoplastic left heart syndrome. And as a consequence, we don't really have very good animal models. There is recently a publication in Nature where they have actually created mice with hypoplastic left heart syndrome, but it's tricky to use them as a model to protect the RV. What are you going to do if you have a hypoplastic left heart mouse? It's not going to last for long. So you can't really assess how you want to prevent RV failure in a staged palliation model in these mice. And therefore, we never really treat the genetic defect or the underlying metabolic differences that we see in the RV. As I already said, LV and RV isn't necessarily the same. And so many of the information that we have about failure mechanisms that are derived from the LV don't necessarily have to work the same way in the RV. So we hope with our research to identify therapeutic targets and basically create some human data to better understand how to improve outcome in these patients. As a kind of a vision, like what we hope to achieve is to get a better understanding of the timing of intervention, because most of the studies that have dealt with stem cell transplantation, they give stem cells after stage 1, like just before stage 2. And it not only is treatment once most of the damage is already done, but it also is at a later stage where your endogenous repair capacity of the heart is probably way less than if you treat earlier. We want to identify single factors instead of the secretome, because if we want to basically change practice and use regenerative medicine in our patient population, you can't just grow cells and get whatever the cells produce and put it into a patient, because you have to basically go through the whole regulatory process for each cell line you're using, because you never really know what you're actually giving. So you have to, if you're not using a single factor or a mix of just a few, it's very hard to actually give it as a therapy. Next step that we are working on with the group at Keller's lab basically is to get cells that are chamber specific. What many people don't know is that the mix of cells that you're actually giving are pretty immature cells that are a mix of atrial, nodal, and ventricular cells. And that makes not only engraftment pretty difficult, but it may be the reason for more arrhythmia that we see, and it may not actually help the ventricle in the end. And ultimately, as a vision in the long term, it's what I call a ventricular switch. I don't know if it's possible, but it's a long-term idea that we are looking into. If we can actually create left ventricular characteristics in stem cells that we are transplanting, can we change the RV back to an LV? I have no idea, but that's what we have to find out, I guess.
We have time for 2 questions. Any questions?
Yeah.
In a long-term model, like would the idea be to inject cardiomyocytes that are functioning, or cell media that would improve the cardiomyocytes in the endogenous ones of the patients? Like the two, what's the
Can you just repeat the question?
Yeah.
The mic
Okay.
so the-
So I think the key question is if we prefer cells to be engrafted into the myocardium versus if we want to just give factors or any kind of factors that come from the stem cells to improve basically the endogenous repair mechanisms of the heart. I don't have a good answer, and one of the reasons is probably because I'm caught in between. Like I'm working with some people at SickKids that are looking into secretome, basically the factor type approach. And there is, I would say, in the literature, quite a shift towards that approach because as I, for example, showed the study results of the primate study, it's pretty difficult to show long-term engraftment and that these cells actually persist despite seeing an actual improvement from the transplantation. On the other hand, the lab that I'm working in at the McEwen Center, they have shown engraftment and that they electromechanically couple. We'll have to find out what the best approach is. I think as I mentioned, from a regulatory perspective, the secretome, like on commercializing it and getting it actually to the bedside, the secretome approach may be the more interesting one because it's easier to generate it in a sterile and controlled fashion, and you know what you're giving, you know what the effects are. It's better controllable than cells. Alex, speak up.
Very quick. Do you think that the die has been cast? By the time we see these kids, so the heart finishes forming by 12 weeks gestation.
Yeah.
And by the time we've seen them, their phenotype has already been determined. In the ideal state, do you think that instead of working at injecting whatever product you come up with in the first stage, do you think that it's a bit late and that we should actually be looking at doing it in fetal life?
It's hard to tell. It may be better, like especially looking at studies where they ablate fetal myocardium. They basically genetically modify them and can switch on that a part of the myocardium basically just dies off. Like studies have shown that up to like 60% of dead myocardium can be replaced during fetal life. They do it very early, but I'm pretty sure from a regenerative potential type of view, like the results would be better if you could treat it earlier. I think the downside is that we don't really know what causes hypoplastic left heart syndrome, with these groups fighting over a hemodynamic reason versus a genetic reason. And before we don't really understand what the reasons are, it's really tough to say what we are targeting during fetal life.
Christoph, thank you so much.
Thank you too.
Oh, his picture's messed up. I don't want that.
No, it's just because it's the online computer.
Okay, well, while Iqbal's going to prove to us that he knows what he's doing with the computer, I'm going to introduce him. If I can see what I'm doing here. So Iqbal Jaffer is a resident in cardiac surgery at McMaster University, and he's spending a little bit of time with us here at Sick Kids. I was introduced to him by Michael Alice Moga one evening when they were bringing a patient back from the operating room. And she said, oh, I know just the person you should talk to, Iqbal, about platelets and surfaces and sticking, which has been the principal research work that I've done over the years with Dr. Bartlett in the lab. So Iqbal is going to try to get his device to work here. And as he works at that, he's going to talk to us about the future of medical devices, but looking at it from making them more biocompatible and sort of going through a few of the challenges with that.
So I want you to know that this is supposed to look like the Back to the Future font. And it works brilliantly on my computer, but my computer doesn't work brilliantly with this lectern. Good morning. These are my disclosures, not relevant to this talk. So polyethylene terephthalate, polytetrafluoroethylene, pyrolytic carbon, polyvinyl chloride. These names may sound unfamiliar, but if you work with cardiovascular disease, then you might know them by another name. So polytetrafluoroethylene is Teflon conduit. Polyethylene terephthalate is Dacron. Pyrolytic carbon is the substance that makes up mechanical heart valves. And polyvinyl chloride is the tubing for ECMO and bypass circuits. Now, apart from having long names, the other commonality between these things, apart from that we also use them in cardiovascular disease, is that they clot. And the reason they clot is because, as an example, they activate factor 12 in the coagulation system, which then activates factor 11, which then leads to clot. Now, there are 30 independent mechanisms in between factor 11 and clot, but this is basically the initiating steps. So, my job is to talk about the modification of these devices and how we deal with them, not only now, but how we're going to deal with them moving forward. And because this is supposed to be sort of future-looking, I'm going to talk about some of the things that we've done that have set the basis for some of the things that are coming forward. So if you have a clot and you want to not make that clot happen, you have two options. You can systemically anticoagulate and inhibit factors along the coagulation cascade, but the outcome or the negative outcome of that option is always bleeding. The other option is you take your conduit and you put a surface on it, which then prevents it from being recognized by the coagulation system, which then prevents clotting. So I want to talk about both those aspects in this talk, but we will deal with one at a time. So if we talk about anticoagulants, we have basically three age categories of anticoagulants. We have the older generation, heparin and warfarin, represented here by Grandpa Simpson. And like Grandpa, they are well known to us. They've been around a very long time. We know how they work. We know what their characteristics are, but sometimes they can be grumpy. And by grumpy, they have complications. They have multiple drug-drug interactions. They have food-drug interactions, and they're hard to manage. More in the middle age, represented by Homer over here, we have drugs like low molecular weight heparin, fondaparinux, and bivalirudin. And in the new generation, we have drugs like the direct oral anticoagulants, dabigatran, rivaroxaban, apixaban, edoxaban, and betrixaban. Now, as exciting as these drugs are, as they're pushing the frontiers of anticoagulation medicine and managing diseases that we never could manage effectively with heparin and warfarin, these drugs, both Homer's drugs and Bart's drugs, are not effective for medical devices. So the reason that is I told you that medical devices activate factor 12, And what happens then is it activates factor 11, which activates factor 9, which activates factor 10, which activates thrombin. And what happens is that thrombin feeds back and reactivates factor 11, generating more thrombin generation. So the only drug currently that we have available that suppresses factor 11 is heparin. But it's this step of activating factor 11, which I believe is crucial to this whole cascade mechanism of clotting on medical devices. So what you do then, if you think it's such an important step, is you suppress or eliminate factor 11, and then you never actually generate sufficient amounts of thrombin. And so what we did was we developed a model using a mechanical heart valve where if you use normal plasma or factor 7 depleted plasma, shown in the red or black, you actually make normal thrombin generation. If you deplete factor 12, you prolong thrombin generation and you suppress it a little bit. But if you deplete factor 11, then you do not generate thrombin. So, if heparin's the only way to do it, what are we going to do? Well, there's a new drug that's actually reached phase 3 studies now. It's an antisense oligonucleotide, which is a small molecule which interferes with mRNA transcription in the liver of whatever its target. Now, antisense oligonucleotides are used widely in lipid reduction therapy for patients with familial hypercholesterolemia, but the application in coagulation is fairly new. And so using this, what you do is you preload a patient for several weeks. It takes about 3 weeks to suppress the levels effectively across the range. And you give them 2 IV injections a week of this antisense oligonucleotide, and it suppresses the production of the coagulation factor of interest, in this case factor 11. Then what you do is you put them through surgery. And then after surgery, you continue on with the therapy. Now, having factor 11 suppression before surgery sounds terrifying, but they go through surgery and there's no excessive bleeding, and postoperatively there's no excessive clotting. The reason being that factor 11 is not actually involved in normal hemostasis. It is involved in provoked hemostasis, but even in this was a knee surgery model, it didn't seem to be of issue. Now, this drug has reached phase 3 studies, and along its coattails are several other small molecules being developed by the big pharma companies that are actively looking at suppressing factor 11 or inhibiting factor 11. So that's from the coagulation side. If we switch gears now and talk about coatings, the key to the concept of coating is to prevent the coagulation system from recognizing your surface. So this is a video from a lab that we worked with at McMaster. And so I'll just orient you to it. In the left corner, it's a regular catheter used in coronary angiography, and this is an uncoated catheter. Then in the middle is the same catheter coated with a older generation coating, and then in this in the rightmost side we have a omniphobic coating that we developed, which is it's gas deposited onto the catheter and then it's lubricant activated. So the reason to tell you that is what you can do is you can take any surface, gas coat it, and then put it on the shelf. And then when you need it, you take it off the shelf, you activate it with the lubricant, which takes about 30 seconds, and then it's ready to go. And so I'm going to show you what happens. So you put a drop of blood on the uncoated catheter, and it sticks. You put it on the previously coated catheter, and it sticks. And if you put it on this omniphobic coating, it just falls off. It's kind of like those Rain-X commercials that for your car. And if you look below the electron micrographs, this is basically thrombus on the surface. And you see that the omniphobic coating actually doesn't modify the surface, and no clot actually sticks upon it. So this coating is actually moving along very nicely and is coming along to commercialization. But you can imagine setting up setting up an ECMO circuit or a bypass circuit not needing heparin if nothing's going to stick to it. The holy grail, however, of medical device coding is this concept of biomimicry, where if you can get the surface of a device to be unrecognized, like normal healthy vasculature is unrecognized, then you never need to worry about it clotting or stenosing or any of that. And the way you do that, or the way you achieve that, is through endothelial ingrowth. Now, most surfaces do not actually achieve a healthy surface of endothelium. And the reason is because they just layer layers and layers of clot upon each other. But what you can do is you can lay down certain ligands which will then signal towards endothelial progenitor cells, which then create a normal healthy endothelium which will actively resist coagulation. And so many groups are actually working on this pathway. The difficulty with this, the ease with this is that it's reasonably cheap to do. The hard part is getting the ligands to stick and to actually target the cells that you need. And it can't be done very easily in moving devices. So you can do it in catheters, you can do it in conduits, but it's hard to do in devices that move. So one step on from that is actually obviating the need for artificial conduits and growing conduits that are suited to the patient themselves. So what you do is you extract cells, you grow them in culture, and then you mix them with a growth medium and you grow them in a bioreactor. Now, if you want them in a particular shape, you give them a porous scaffold and you inject them into the scaffold and then you grow them in the bioreactor. Now, this is very exciting, but it's very costly and it takes a lot of time. One step on from that is you actually 3D print what you need. And so you can print a 2D sheet, which you then roll on a mandrel, and then you create a conduit like that. Or you cell by cell 3D print conduit, or a whatever, for whatever patient you need. And the advantage of this is obviously you can build all sorts of shapes and sizes that you need, which would obviate the need in children for repeat surgeries just for conduit changes. It would obviate the need for anticoagulation. And because this tissue is alive, it would grow. Now, if this all sounds very far-fetched and whatnot, just think where we were 50 years ago and the kind of things that if I had talked about them 50 years ago today, people would have had their minds blown. And just know that my wife, who's not a scientist, has already mastered human cloning. Thank you very much.
Questions? No questions? I have a question.
Please no. Yes.
So, if you were to use your surface, the one, the non-stick surface that you created, and if you were to use it, can you apply that to any type of polymer, or is it
Do you need a glue?
specific?
No. So we have worked with coatings that you need a glue for them to stick, and we've used this coating so far on the PCI catheters, which are made of a version of polyvinyl chloride. We are currently doing experiments right now where we're working on coating Teflon and Dacron conduits, and it seems to stick without any glue. There's a machine that gasifies the substance, and you put whatever you want in there, and it gasifies it, so you get inside and outside coating, and it seems to work. The question is whether using needles and putting suture through it would actually rip the coating off.
And then what about an oxygenator or a dialysis membrane?
That's our next step. That's our next step. Yes, Alex?
How long would it take to actually print
Mm-hmm.
in a completely structured conduit or valve? Like, how quickly can you go from harvesting the cells to actually having a finished product?
I don't think anybody knows the answer to that. Grey's Anatomy thinks it's 16 hours. because there was an episode about that. But Iqbal doesn't know the answer to that. The reason being that there's multiple elements to 3D printing. Current 3D printing technology is single polymer based, and in humanized or living conduits, we have multiple cell types and we have multiple structures. I actually think out of those futuristic-y sort of options, the pre-made scaffold, which you inject cells, which become confluent, you grow them in a bioreactor, is actually the most ahead and is the most likely to come through. They've done that with, they've decellularized kidneys and have recellularized kidneys. They've decellularized lungs and recellularized lungs. Teeny mouse lungs, teeny mouse kidneys. But at least the proof of concept is there for those where the structure already exists. I think that bioprinting or 3D printing multiple cell types, multiple structure types is going to be a bit more challenging.
All right, guys. It's the future.
Good morning. It's my pleasure to introduce the Pasquale family. Manfredo Pasquale and his wife, Linda Cassano, are here today, and they're here to share some of their story about their son, Tommaso, who's 10.5 years old and is one of the most courageous and well-spoken grade 5 students I've ever known. And he has quite an incredible story and has recently done a Sick Kids fundraising campaign at his school, which exceeded his very sizable objective for fundraising. So Manfredo, thank you.
Thank you very much, Kathy. Can everyone hear me okay? Okay. Before I begin, I'd just like to start off by showing everyone a video. And I'd also like to say that I'm truly humbled and honored to be here this morning and to share with you my family's story. So let's just take a look at the video first.
Thanks, guys. My name is Tommaso Pasquale, and I'm
Put it up.
as you all know. I am very active and I love to play sports. Especially, I love to play sports. I love to play soccer and throw hockey with my friends. One of my personal goals this year is to raise $1,000 or more for Sick Kids Hospital in Toronto. And I need your help to get there. Sick Kids is a very special place for me, as you all know. I received the best care in the world when I was first born, and I continue to receive amazing care for all of my fellow medical visits. I want to raise this money to help other children and their families be healthy, active, and happy. My journey at Sick Kids begins when I was first born. I needed 7 operations on my heart. When I was a newborn baby, I continue to receive Sick Kids. I continue to go to Sick Kids on a regular basis for checkups and to make sure I continue to stay healthy. Here are some pictures of my last visit this past fall. This is me and my dad before I go to the hospital. Say hi, Dad.
Hello.
Here are some random pictures before my procedure. My first visitor! This is me. This is me in bed before I go into my procedure. This is me in the recovery room after my procedure. As you can see, I brought my favorite blanket. Go, Leafs, go! My favorite part was when my crazy uncle came to visit me, and man, this guy is hilarious. You guys like that video, right? A few weeks ago, each of you received a fundraiser package to help raise money for the new Sick Kids Hospital in Toronto. And it's my goal. Wait, did I say my goal? I mean, it's our goal to raise $1,000 again for the new Sick Kids Hospital in Toronto. But I can't do it on my own. I need each and every one of you to raise as much money as you can. We will be also having a walkathon on Friday, March 9th, 2018 at 9 o'clock. Teachers, could you please keep your students' information forms? Can we do it?
Yeah!
I would like to personally thank Miss Rhea, Miss Muir, Miss Tipu, and the Parent Council for all their help in making this happen. Especially I want to thank my fellow students at St. Stephen's School. Thank you very much, and have a great day, guys.
The video you just saw was of our son, Tommaso. Tommaso's sick kid's journey began just a few hours after his birth. Struggling to breathe, he was rushed from his local hospital to the NICU at Sick Kids, where it was discovered that he had hypoplastic left heart syndrome and would require several open heart surgeries. My wife and I were first-time parents and instantly fell in love with our newborn baby. It was terrifying to hear the news. And the most challenging moment in our life. At 7.5 months old, Tommaso required a heart transplant and spent a considerable amount of time in the critical care unit. Today, Tommaso is a happy and active 10-year-old who has an abundance of energy, a passion for soccer and the Toronto Maple Leafs, a love of school, and a desire to help others. This past fall, he was admitted to the hospital for a bronchoscopy. Did I say that correctly? I believe so. And after that experience, when he came out from the hospital, he says, "Mom, Dad, I really want to do something for the hospital, and I want to do a fundraiser." And so he came up with the idea, and the idea was a walkathon to raise money for the new Sick Kids Hospital. His goal was to raise $1,000, and with the help of his school, friends, and family, the total raised for Sick Kids was $7,800. He was so proud, and so were we. On the 10th anniversary of receiving his new heart, Tommaso chose to visit Sick Kids and arrived at the hospital to present his $7,800 donation. We were later asked if we would be interested in speaking at this symposium and to share our overall experience with Sick Kids while our son was here and continues to come here for clinical visits and checkups. I jumped at the opportunity to do this because, after all, we would do anything for Sick Kids and saw firsthand the quality of care that takes place here. Unfortunately, Tommaso felt a bit shy and opted not to be here, and so on behalf of him and the rest of our family, I would like to offer some words of encouragement to all of the doctors, nurses, and staff that looked after our son while he was here at the hospital. Continue to do your work with passion. Continue to strive for new and improved medical practices and frontiers. Continue to provide the exceptional care and comfort to patients. And finally, continue to save lives and provide hope for other families and children. Thank you. If anyone has any questions about our overall experience at the hospital or what it's like having a sick child, I would be more than happy and open to answer any questions.
Question for you. My name is Peter Lawson. I work in the cardiac ICU. So in 10 years' time, we hope to have a new intensive care unit and acute care facility open. What would you want to see as integral components of that might have helped Tommaso and yourself?
Well, they did make one fix when we were there the first time, and they put in some nice new sofas. So, you know, I think that, you know, obviously within the medical community, the medical professionals have a way of making ease on the patient and all that kind of stuff. And, you know, you want to make ease on the family as well. So by providing them as comfortable an area to sit around and wait would be job number one. In terms of making improvements within there, I really can't speak to anything because, and it's not because I don't have an answer, it's because we had an overall very good experience there. You know, the doctors, the nurses, the staff were all very informative. They walked us through each process, and a lot of the talks that they had, as you all know, are not very easy to have. And they were all very comforting, and I don't think we had any issues whatsoever, to be perfectly honest with you.
Thank you so much for coming today. We're so happy that you've been involved. I've got a statement and a question. The statement is, I think he needs an agent.
I've been mentoring him slowly, Georgia, okay?
I think that, you know, you could make a lot of money there. But the question is, if you could speak to, like, obviously it was a very distressing time when Tommaso was very first diagnosed as a very small baby, unexpected. What advice would you give to another family going through a similar situation?
It's a very, for me, it's a very easy question to answer. And the advice I give a lot of my friends and people that I talk to, and it's to really follow the path of what the hospital tells you. I think that when you're under a lot of stress and you really don't have any clarity, it's very easy to make decisions on your own without thinking things through. And ultimately, I'm not a professional. I've been listening to you folks for the past 2 hours, and I probably understand about 5% of what you're saying. I do understand what you're doing, but I think that families need to listen to the doctors and kind of take that notion that they don't know what they're doing, and that's why this exists. And ultimately, we're very fortunate enough to live in a country where things like this are possible. So that's the piece of advice I would give in that. Anything else? Okay, thank you very much. Thank you very much.
Uplifting story.
Thank you, thank
and
you.
Very encouraging.
Thank you.
So I'm very pleased to introduce our next speaker, Azadeh Asadi. And Azzy is a pediatric nurse practitioner in the cardiac critical care unit at Sick Kids. And she's also pursuing a PhD in biomedical engineering at the University of Toronto, having earned her master's in nursing in 2016 from the same university. She also holds 2 bachelor degrees, one in science and another in nursing. And at Lawson Labs, Azzy is developing an online application that would facilitate the acute care management of pediatric patients with congenital heart disease who have been discharged from the intensive care unit. She applies her clinical expertise in data labeling and classification with research interests in clinical translation engineering. So please welcome Azzy.
Thanks, Cecilia, for a very kind introduction, and thanks for having me. So today I have the opportunity to talk to you about one of the things that Cecilia talked about, being the application that I'm trying to develop for patients who are discharged from the cardiac ICU. But before I go into it, I was told to confess to the fact that I have no conflicts of interest, so it's on a slide. But I'd like to lay the lay of the land a little bit. It's not a secret or a surprise that kids with heart disease are actually at a greater risk of cardiopulmonary arrests, given their physiology. And in fact, research has shown that when you compare kids with heart disease and kids who do not, kids with heart disease have a 10-fold higher incidence of having a cardiopulmonary arrest than kids who do not. And when you compare the data from the cardiac ICU to the pediatric ICU, the rates vary from 4 to 6% in the cardiac ICU and 2 to 4 in the peds ICU. Similarly, you can see data that sort of pick up on the incidence of cardiac arrest in the cardiac OR and in cath lab being at 0.2% and 0.7%. Moreover, from the same broad category of kids with heart disease, children with single ventricle physiology are at a higher risk of not only experiencing significant cardiopulmonary arrest, but also suffering morbidity and mortality from it. And in fact, these kids overall are more hemodynamically unstable and are easier to sort of deteriorate at the face of common childhood illnesses. We know this based on some of the data that comes from the SVR trials showing that kids who are in their interstage sort of phase following their Norwood procedure have a 12% mortality rate, and that kids who are already in hospital, in a single ventricle hospital with a Norwood physiology following that surgery, have a 74% chance of mortality while they're still in hospital, which is a huge percentage. 20% of kids who are in their interstage following being discharged home present to either emerge or suffer an event at home following which they can die. And in many of those kids who present to emerge, many of them present with respiratory and GI symptoms, which are often sort of under the umbrella of heart failure and can go unrecognized, being chalked up to regular childhood illnesses. Kids with congenital heart disease have a, where is it? Hold it. Okay.
You can just put it on your line.
Oh, so I can walk?
Yep.
Perfect. Thank you. Sorry about that. So kids with congenital heart disease are harder to resuscitate. And that could be due to several factors, one of them being that they have anatomic limitations to having an effective stroke volume. So if you have aortic regurgitation, for example, in the setting of CPR, they would have impaired flow to their systemic perfusion. You can have limitations to their pulmonary blood flow based on, again, their anatomy, if they have pulmonary hypertension, if they have a BCPS physiology or physiologically have pulmonary hypertension. They can have limited cerebral blood flow in the setting of CPR, which could compromise their brain recovery, again, in the setting of BCPS or Fontan physiology. And of course, many of them have airway abnormalities and, of course, several clots following procedures that would limit access to their vasculature. In addition to all of that, there is a knowledge gap that exists when you consider clinicians who are non-cardiologists and non-cardiac intensivists that would compromise and affect how well we resuscitate these children. There was a study done of all the emergency physicians in the state of Michigan that showed that about 72% of them were actually uncertain about what the saturations should be for a child with single ventricle physiology. And 58% of them were uncomfortable or worried about the treatment they were providing, which is a significant amount. 59% of them didn't believe that education on its own would be sufficient, but if you take that in light of the fact that many of these peripheral hospitals do not necessarily see as many of these single ventricle patients, education on its own would make sense to not be sufficient. And even if you do have the knowledge, accessibility to sufficient information during an acute situation in and of itself is also very limited given the current system of information transfer that's available. If you consider when we communicate on rounds with each other, oftentimes we use a lot of terminology and eponyms to describe a child's physiology and anatomy, and many of these are unfamiliar to people who do not strictly come from cardiac background. In addition to that, understanding the physiology in and of itself is another layer of complexity that requires another layer of training and expertise to be able to translate the anatomy to what the physiology of a patient is. handover process in and of itself has been identified as a high-risk procedure that is subject to recall bias and inaccuracies that are sort of portrayed as two people exchange information. Oftentimes, rationale for decisions are not relayed in handover practices, neither are anticipated problems for each patient. So the solution? We set out to solve at least the last 3 points that I talked about, being that we proposed that we could have a web-based solution whereby we could transfer information electronically in such a way that's more efficient and timely. We set out to transfer knowledge to address the knowledge gap by virtue of not only relaying the anatomy of a patient, but also trying to capture their physiology and their functional state. And lastly, in the setting of an acute event, we set out to provide some guidance around how to resuscitate these children effectively by means of providing personalized information. So my heart path looks something like this. This is a screenshot of what the application would look like and the information that's embedded in it. And I will walk you through it because that is too tiny. So from the top, we start by trying to capture the demographics of a patient, but more so trying to capture their resuscitation status, what their airway is, as well as some sort of guidance around what the expected saturations, blood pressure, and heart rate for a patient who has left the ICU has been, and what you expect it to be for that child to be stable. In the next phase, we talk about what the patient's heart looks like, and this is where we try to address the knowledge gap. So visually, we try to capture what the anatomy of a patient's heart would look like, and then side by side to that, we capture some functional data in terms of, for example, if there's regurgitation across the valve, or if there's poor function on a ventricle, or both. And on the far left, I guess, for you, or far right for you guys, we try and capture the physiological state of a patient. So talking about what the systolic function is, and if it's a systolic dysfunction issue for this patient, then we try and provide some guidance around, for example, not fluid overloading them or considering some inotropic support if they're in trouble. In addition to trying to capture the heart, we try and capture some information about, for example, what their expected baseline heart rate or heart rhythm would be. And this is, again, based on some of the data that we have that we physiologically collect from our bedside monitors, and we can just translate it into this application. In addition to that, we talk about, for example, where are the vessels that are occluded so that we can bypass the process of trying to discover which vessels should be used for access, as well as talk about what medications a patient is on and if they're paced or anticoagulated. And then towards the end, when we one of the other issues that I talked about was around guidance in the setting of acute events. And so one of the second last parts of the application addresses specifically that if you have a patient who presents an acuity and in extremes, these are the things that you should consider in the pre-arrest, arrest, and post-arrest phase, with a lot of emphasis being put on good quality CPR, as well as a focus on drawing attention, especially the attention of peripheral hospital clinicians, to considering what the limitations to successful resuscitation of a patient would be, to then trigger the thought process of trying to get help from other tertiary institutions with more specialized care. On the far right of your screen, you'll see some information with respect to cannulation details in case a patient presents to a hospital that's not familiar with pediatric ECMO cannulation. And then the last piece involves trying to get families involved into caring for patients and being on the lookout for these patients deteriorating before they become acutely ill. And so in this section, not just for families, but also for general pediatricians, we talk about some of the symptoms that resemble normal childhood illnesses. And in that setting, we then sort of ask for people to be vigilant for these symptoms and always consider heart failure as part of their diagnoses or differential diagnoses. So so far, this is where we've come. We have a sort of a beta test of it, I guess, on the works. The idea being that now we are considering to do some heuristic testing to make sure that the application is user-friendly and that it could be used not just by specialties, but also by the target people that we are trying to capture and enrich their knowledge base. Following that, we will consider doing a low fidelity and a high fidelity simulation-based testing, and then look at implementing it into practice. When all of that goes through, the idea would be to translate it into a mobile application that patients can carry on their phone or parents can carry on their phone and have it as a tool whereby they can present information to various clinicians. And then since we're looking at futuristic work, things like having, for example, QR bracelets with a link that is secure to this application for each patient that could be accessed by a clinician in a peripheral hospital where if you assume a patient sort of is presented to them unconscious or unable to present their information on their own. Finally, we want to look at expanding into other pediatric institutions and also trying to capture the adult congenital heart patients who are probably one of the most at-risk populations because it's so rare for them to present to the adult world with a congenital heart disease, given that only recently they're making it into adulthood. So, children with heart disease have complex heart, which we know. They're difficult to understand and conceptualize, and they're very difficult to resuscitate. And we're hoping that with MyHeartPass being an electronic solution, we are applying a human factor approach and a multidimensional approach to try and solve the problem holistically. With that, I'd like to thank the awesome team that I have the privilege of working with. Without them, none of this would be possible. Three of them are sitting in the room. And that would be it for me.
So thank you, Ezzy. That's truly exceptional work. I would like to ask anybody in the audience if they have a question for Ezzy. Questions?
Yeah.
Thank you so much, Ezzy. Thanks for coming and speaking to us today.
Thanks for having me.
This seems amazing and logical and useful. So why don't we have it already? What's the hold up? What's stopping you from actually
Putting it out there?
this and having it available now?
So with any application and with anything new that's of a engineering origin per se, I think it's important to make sure that it fits into practice and it fits into flow. And what I mean by that is, ideally, if you consider the workflow that happens in the unit, it's important to consider who populates the information, where the information comes from, and how we keep it up to date. In addition, it's also important to make sure that we don't overwhelm someone who doesn't come from a cardiac background with the information that we're presenting them on a screen. So going through all of that, we thought it was important to try and capture their opinions and their input into the design of the application. So this has some heuristics incorporated into it. It has some opinion from sort of certain groups of stakeholders incorporated into it, but it's still not quite taken the opinions of people who I think will be using it and relying on it most. What I mean by that are general pediatricians, for example, emerge physicians, residents, people who are less versed in the lingo per se than we are. And so to do that, part of the study going forward is to try and get their opinions into it and try and put it into simulation to prove that, in fact, having a device like this would actually increase the accuracy of your diagnosis and also how quickly you recognize what's happening and how comfortable you are leading a team, things like that. Yes?
That was an excellent presentation. Thank you very much.
Thank you.
I think your main application will be the adult world. I would be tickled pink if all my adult congenital heart patients had this on their cell phone. Many patients confuse the name of their surgeon with the procedure. I just have a little difficulty visualizing when you leave the PICU at Sick Kids and go to the ward, is this a dashboard in the electronic medical record, or is it something that you give the parents to have on their phone?
So the idea is, The idea is for all the information to come from our current existing database that we have on our patients. So because
Yeah, I
it's...
understand, but where's the platform to
So it will sit here. That's what I'm trying to say. So it will sit, the data will be housed within this building, within our EMR system. The platform, right now, the version that we have is a desktop application. Moving from that, we'll go to each patient's cell phone, and then from that, we'll go to the bracelet where a clinician could scan and see it on their phone, so that we could find a way to validate, like ensure privacy, validate who they are, and then be able to see it. So we're going to break it into chunks and make sure it works at each step before we sort of implement it further out. Does that answer your question?
No, it introduces lots of possibilities.
Mhm.
But, I honestly think your main impact will
Mhm.
eventually be the adult world, the transition
agree.
population.
Yeah, I agree.
And it would be nice to empower teens to own more of it.
Mhm. Yeah, no, I agree.
You talked about there being an education gap with the adult population general practitioners, but I also wanted to mention as a bedside nurse how important this is going to be for families.
Mhm.
We do our best to communicate with them at the bedside about what's going on with their child, what their special health concerns are, but putting that in the hands of a family caregiver who will then be able to give that information to their child as they grow up to take care of themselves.
Mhm.
This is so impactful.
Thank you. No, it's really neat if we could. The idea is increasing access to information, essentially, right? And by doing that, you can then open, even if the information on the actual application isn't educational, you open the door for a conversation and for an educational moment, which in and of itself is of value. Did you want to?
My question was just with respect to the identified knowledge gap in providers and also in families, and trying to get some more clarity around these issues. When talking about how this will look, I think you had mentioned that there would be the ability to learn about the different diagnoses through this platform, but I was also wondering, is that going to be targeted towards healthcare providers or towards families, and how is that going to look in terms of being able to learn more about a cardiac diagnosis or a cardiac surgery through this platform?
So when we talk about learn, it's not to the effect of a critical care fellow going through cardiac ICU training. The idea is to try and portray, a certain anatomy is associated to a certain name and is at risk of a certain series of issues, and then be able to relay the fact that, for example, if a patient presents in systolic dysfunction, these are the things you should consider first, and these are probably the things you should avoid, and be able to slowly associate one to the other. And it comes down to how often you get exposure to a patient to these patients. In a peripheral hospital, you may not, and it could just be a one-time or a two-time use reference to the application. But in our institution, for example, it could be referred to more and more often, and it could be used as, like I said, even just an introduction to a series of questions and a learning opportunity. Does that answer your question?
So thank you very much. That's
totally didn't have to.
incredible
Thank you.
work, and we can see that you and your team have done a lot of work for it, and we look forward to it.
Never not embarrassing. Never not embarrassing. I was given the sort of almost sadistic brief of talking about hemodynamic monitoring in a half hour, and trying to think about what we'd talk about rather than talking about very complex things that are interesting that we might not encounter in practice, like Vigileo monitors or PA catheters. I wanted to try to make this very practical and focus on the devices and the data that we gather when assessing the hemodynamic state in patients on a day-to-day basis. And wanted to start out with a very obvious observation, which is that instability is a late sign. I think of instability of a hemodynamic nature existing in one of two scenarios in critical care. One is the sort of very unfortunate hand of God scenario, where you suddenly are dealing with an unheralded lethal arrhythmia or unheralded catastrophic bleeding, and by definition, in scenarios like that, you're in a reactive mode. But that's the minority of cases of hemodynamic instability. The majority of cases evolve gradually. And if you are a thoughtful consumer of the data that you can get from the bedside, there are many clues as to what you can modify about the hemodynamic state, what you can incorporate in your therapeutic strategy, modifying intravascular volume, systemic vascular resistance, cardiac output in a way that prevents instability from developing. And so we'll have that as the frame of reference when we go through this presentation. And as a point of departure, there are certain questions that I always ask myself when I'm taking care of someone who I believe to be at risk of hemodynamic instability. The first is, what sort of problem do I imagine I need to actually monitor for in this patient? How do I imagine they would become unstable, and why? And that then informs the next questions, which are, what's currently being monitored, and how does that compare with ideally what I think I should be monitoring in order to pick up the problem that I need to monitor for? The fourth question is one that should be a continuous question in critical care, and that's, what am I monitoring vulnerabilities? And this differs a little bit from the previous questions in that what you're talking about when you think about monitoring vulnerabilities is ways that you can be misled by the data you have. So you might have all of the monitoring devices in place that you would want, but because of artifact or some other aberration in the data, you might go down the wrong track. So starting with non-invasive monitoring and starting with things that everybody gets, and then moving through invasive monitoring and things that select subpopulations get, we'll first talk about the clinical exam, for which there is no replacement. Can't emphasize the importance of the clinical exam, both in forming the hypothesis about what you think is wrong with the circulation that then you use data to confirm, or refuting the hypothesis that you've generated by consuming the data. And there's one specific aspect that I wanted to emphasize in talking about this, and this is the thermoregulation that patients with fragile circulations are less capable of than the general population. The body is extraordinarily effective and efficient at maintaining body temperature within the narrow range where we optimally function. And one of the mechanisms by which this is accomplished is countercurrent heat exchange between arteries and veins. It's one of the reasons that the veins travel with arteries in vascular bundles. And the way that this works is blood leaving your core is radiating heat, which veins can pick up, traveling in the opposite direction to return to your core. The mechanism is much more efficient over extremities than it is over the core. And that's where the majority of heat radiation occurs, because it's a surface area to volume ratio dependent phenomena. When you have a decline in your cardiac output, the two special circulations that the body's very effective at sacrificing early in order to try to centralize blood volume around your vital organs, brain and heart specifically, is the splanchnic and cutaneous circulations. And so vasoconstriction that occurs as part of this, this adaptive response is more marked in extremities. The consequence of that is that you radiate heat much less effectively. This mechanism that is adaptive under normal circumstances becomes maladaptive and concentrates heat in your core. And this is the basis of the inability of patients in low output states to effectively dissipate heat. And this creates a clinical sign that cardiac intensivists, I think, maybe more than almost any other group, almost compulsively rely on. And that's the gradient between your core and your peripheral temperature. You see people on rounds reaching out and feeling toes and fingers for this reason. The data on this is a little bit uneven, but as a general point, the gradient between your central and your peripheral temperature, or your core and your peripheral temperature, correlates positively with your systemic vascular resistance across patient cohorts. So as your SVR goes up, the gradient between core and peripheral temperature goes up. In patients with a fragile cardiac output, that can indicate a falling cardiac index, because part of the adaptive response to a decline in your cardiac output is an increase in your systemic vascular resistance to try to maintain organ perfusion. So cardiac index is inversely correlated with the core to peripheral temperature. And the obvious vulnerabilities in making these assessments, so pharmacological effects, you might just be on a whole lot more SVR augmenting agent than you should be. Environmental effects, maybe the room is icy cold, et cetera, et cetera. But this is one of the key physical examination findings that many of us rely on at the point of care. Moving on to something else that everybody gets or should get, and that's a non-invasive blood pressure. Classically, this is either done with palpation or auscultation. However, we increasingly rely on the sort of oscillatory measures that we have available to us with these automated blood pressure cuffs. And it's important to know exactly how those work so that you can understand how those can potentially lead you astray. The technique relies on fuzzy logic to inflate the cuff to a pressure higher than it imagines the systolic blood pressure is going to be in the limb, so cessation of arterial flow, and then incrementally decreasing the pressure in the cuff, typically in about 4 millimeter increments, until flow is restored. And just before the onset of systolic flow, you start to get vibrations in the blood vessel wall that cause oscillations. With the onset of systolic flow, those oscillations are vibrations and cavitation of the vessel. And those oscillations continue down below the diastolic pressure. And so if you modeled it, it looks something like this. Oscillations that begin above the systolic and go below the diastolic. The oscillations are maximal at the mean arterial pressure. And so what these oscillatory cuffs measure accurately is the mean blood pressure. They then use an empirically derived algorithm to estimate the systolic and diastolic blood pressure. And so it's important to recognize what's being measured and what's being estimated using this measure. And that would explain what your vulnerabilities here are. You know, in anyone who doesn't have pulsatile flow, so for instance, a patient on a VAD who has non-pulsatile flow, this method won't work. You can't generate a blood pressure using a cuff under those circumstances. Arrhythmias that cause very chaotic and variable oscillations in the blood pressure and the pulse wave in the arterial tree will also be associated with very impressive artifacts and erroneous measures using this technique. And then in patients with increased arterial stiffness, in which the oscillations are attenuated, you are also going to introduce error into your assessments. So continuing, again, with more non-invasive stuff that everybody should get, either as a continuous or as an intermittent measure, pulse oximetry. It's something we're all familiar with. The way we use it in the unit here is transmissive pulse oximetry, where the light-emitting diode is opposite the photodetector. And the red and infrared wavelengths that are emitted are variably absorbed by oxyhemoglobin and deoxyhemoglobin. It's important to recognize that pulse oximetry relies on the weaker pulsatile component. The pulsatile component of this signal is about 100 times weaker than the non-pulsatile component. And that means that pulse oximetry is much, much more susceptible to changes in perfusion than, for instance, NIRS monitoring is. It's also important when you're assessing the circulation using pulse oximetry, and that's maybe an obvious observation to this audience, to remember where your probe is placed, because that gives you important information about how the circulation is working in a very general sense. You know, we've all seen situations where people are, for instance, responding to a postductal saturation with recruitment maneuvers in a patient who's known to have an obligate right-to-left shunt at the ductus arteriosus. You want to make sure that you understand where the probe is placed and what that should be measuring as a result, based upon your understanding of the patient's circulation. Vulnerabilities here are the ones I've already mentioned, so your susceptibility to perfusion. We all know how sensitive these are to movement. It's also important to recognize, however, that what you're measuring here is arterial saturation. You're not really measuring arterial oxygen content. And one of the scenarios in which you can be misled by saturations in patients who are very anemic. The hemoglobin is fully saturated, but there just isn't enough of it to guarantee adequate systemic oxygen delivery. So keep that in mind. And then there's some characteristic artifacts associated with metabolic poisoning, so carbon monoxide, cyanide, methemoglobin. I'm not going to belabor NIRS. This is a more continuous measure than what we've talked about until now, and is generally something you're going to deploy in patients who you're more concerned about than the average patient. This is a technique that relies on the relative transparency of tissue to infrared light, and again utilizes absorption spectra to make a determination about the relative proportion of oxy and deoxyhemoglobin. The interesting thing about NIRS is you're utilizing the non-pulsatile signal, as I mentioned earlier, and so this is much less susceptible to changes in perfusion. Depending upon where you put the probe, be mindful of how you're going to actually label that. So ScO2 for a cerebral oxygen saturation, the probe is relatively sensitive over depths of about 24 millimeters, so 2.4 centimeters. If you're measuring a renal NIRS, that's essentially trying to estimate or approximate splanchnic blood flow, and then If you see these being used in environments like the PICU where there's a procedure like, say, for instance, limb salvage done, and you're using the probe to estimate a tissue saturation, you'd need to label that differently. But as is often said when NIRS is used to monitor a patient's hemodynamic state, there's an impressive degree of error or margin of error between the value that's reported by this spectroscopic method and the actual directly measured saturation. So it's up to 10 to 15%, depending upon the device. However, the devices are much more sensitive to an actual change in saturation with a much smaller margin of error. So again, point here is utilize it to understand the trend in the saturation that you're estimating rather than believing the absolute value. When you start to invasively monitor hemodynamics in a patient, you're saying, well, two very important things. One is that you need to move from intermittent measures of the hemodynamic state to continuous measure. And the second is you've made the determination that the risks associated with placing the invasive monitor are lower than the risks associated with not monitoring, whatever it is that you're concerned about the patient suffering from a hemodynamic standpoint. And it's important when you're using these invasive monitors that are generally felt to be much more accurate than non-invasive monitors to understand your vulnerabilities here too. Can anyone actually, where do we generally sample a mixed venous saturation? So in a normal circulation, where classically would you sample the mixed venous saturation? Sorry? So is that the classic location? So that's where we sample it because of convenience. But where classically would you ideally sample a mixed venous saturation? Pulmonary artery. And the reason that it's the pulmonary artery is that what you're trying to capture with a mixed venous saturation is the admixture of the three sources of venous return. So the SVC saturation, the IVC saturation, which is typically about 5 to 7 points higher than the SVC saturation because of the effect of the renal veins, that we'll talk about again in a second, and then the coronary sinus saturation, which is actually the lowest venous saturation in the body. And you want to sample, ideally in a well-partitioned circulation at a point where all of these sources of venous return have had the chance to fully admix. Because of problems associated with using PA catheters in small patients, and because of the fact that a lot of our patients have very unusual hearts that are subject to things like intracardiac shunts, we use the SVC saturation as a proxy. But recognize that it's actually not a classic mixed venous saturation. I put the Fick equation up here, so calculating basically cardiac index by dividing oxygen consumption, or VO2, by the arteriovenous oxygen content difference, because it always is helpful to remember that what that equation tells you is that mixed venous saturation is directly proportional to arterial saturation, hemoglobin concentration, and cardiac outputs, and is inversely proportional to oxygen consumption. Because that explains a lot of the interventions that you see people working on at bedsides when patients have inadequate systemic oxygen delivery, optimizing hemoglobin, cardiac output, optimizing the arterial saturation, and if you aren't able to optimize supply, going after demand by dropping oxygen consumption. Again, a simple but obvious point, the AVO2 difference is more important than the absolute mixed venous saturation as a number. If you have a patient with 100% arterial saturations and a mixed venous saturation of 40, that's a different clinical problem than a patient with the same mixed venous saturation and arterial saturation of 60. So you're interested in patients who have abnormal circulations in the AVO2 difference to make a determination about what that indicates about the cardiac outputs. And it's important because of what we've been talking about to recognize what the classic inaccuracies associated with catheter position here are. So if you put in a femoral line, and that femoral line sits opposite the renal veins, you will overestimate the mixed venous saturation. And that's because the renal venous saturation is the highest venous saturation in the body. The kidneys only require about 20% of the blood flow that they receive for their nutritive needs. The rest is there for their functional needs, i.e. generation of urine. And so the amount of oxygen that's extracted from blood going to the kidneys relative to the total amount of blood flow is quite small. The renal vein sat is high, and so if your catheter is sitting in this location, you're probably going to overestimate the mixed venous saturation. Conversely, if you come from above with a long catheter, or you have a long catheter, for instance, like a UV coming from below, and the catheter snakes into the coronary sinus, you'll underestimate the mixed venous saturation because that's the lowest venous saturation in the body. So recognize that there are important classic inaccuracies associated with catheter position. It's also important to recognize that any malformation, vascular malformation, has the effect of introducing potential error as well. So extracardiac left to right shunts, hepatic AVMs, intracerebral AVMs, anomalous pulmonary venous drainage are all scenarios in which you will overestimate the mixed venous saturation, even with what you think is a well-placed catheter. I want to talk, just before we quickly review some of the intravascular pressure tracings on how we transduce pressures at the bedside. Transduction of pressures relies on a strain gauge, what's known as a Wheatstone bridge. Essentially how this works is you have a column of fluid in contact with a silicon membrane. Pressure is transmitted through the column of fluid from the vascular space. It deforms the silicon membrane, which deforms the strain gauge, which changes the voltage difference across the strain gauge in a way that allows essentially a linear relationship to be established between voltage difference and changes in intravascular pressure. And using a strain gauge in this way, you have a very graded and sensitive way of transducing a mechanical signal into an electrical signal that you can display on the monitor. The classic catheter that you would want to use if you were going to transduce an intravascular pressure and believe it would be a short catheter that is as large in diameter as possible to get away with, and that's also non-distensible. And that's because resistance in any tubular structure is a function not just of the diameter, but also the length. The longer the tube is, the higher the resistance at a fixed diameter. This is the reason why things like transducing PICCs is generally not a great idea as a way of estimating the central venous pressure. That's a very long line that's associated with important resistance as a consequence of that. The other reason you wouldn't want to transduce a PICC is it's generally a distensible tube. And we'll talk about that in a minute here. But recognize that in addition to those things, clots, kinks, any air in the line, or underdamping, which is something I'll mention again in a minute here, will lead to artifacts and will lead to you erroneously either under or overestimating, depending upon the nature of the artifact, the pressure that you're transducing. We zero these lines to what's known as the isobestic point. For arterial lines, that's generally the midpoint of the left atrium. For venous lines, the midpoint of the right atrium. There's special scenarios where a classic one would be measuring cerebral perfusion pressures in the PICU, where if you believe that the cerebral venous pressure, for whatever reason, is higher than the right atrial pressure, you zero it to the level of the arterial circle of Willis. So just recognize that you need to be a little bit thoughtful about what your isobestic point is and where your transducer is as you consume this data. But assuming you've done everything right, this is what your classic central venous pressure tracing would look like. And I've tried to synchronize events in the central venous pressure tracing with an EKG signal. There are three phasic plateaus and two descents. The A wave occurs after the P wave on the EKG, and that's associated with basically atrial systole or atrial contraction. The C wave is isovolumic contraction of the right ventricle. And so that's going to occur immediately after the QRS complex, so electromechanical coupling. And this is the phase where the ventricle is contracting, hasn't yet started to eject anything. And as a consequence, the tricuspid valve is displaced up and into the right atrium. And that creates this little upstroke in the pressure wave before the pressure continues to decay. The X descent is best understood as systolic pressure collapse in the atrium. And what that means is basically the pulmonary valve has opened, the ventricle has begun to eject, and the plane of the tricuspid valve moves down towards the apex of the ventricle, allowing pressure in the atrium to continue to fall. The V wave is venous filling of the atrium before the tricuspid valve opens, and then the Y descent is what's known as diastolic pressure collapse. So this is the tricuspid valve is opened, atrial systole hasn't yet begun, but there's passive emptying of the atrium. And if you understand these events and their synchrony with the EKG signal, some of the classic patterns of abnormalities in CVP tracing become apparent. And these are very important to recognize. These would be examples of the kinds of things that I was mentioning earlier as clues as to the hemodynamic deterioration of the patient. If you have a patient with good hemodynamics and a CVP tracing that is classic tracing or the tracing that you might expect, and you come back and you find a patient in low output with fused CV waves, that gives you an indication as to what your problem might be. But Canon A waves, so loss of AV synchrony, the atrium is squeezing against a closed tricuspid valve, causing very, very large A waves. If you have a very leaky tricuspid valve, there's no phase of isovolumic contraction. And so you get a very large C wave that tends to fuse with the V wave. If you have a problem like tricuspid stenosis, so a slightly more subtle problem than the other ones that we're talking about, you accentuate the A wave, and then you flatten the Y descent because it's harder for the atrium to empty. And then if you have someone with a restrictive or constrictive physiology, so you'll see this in the TET patients that we talk about as having restrictive physiology, you get this M or W sign. It's also known as Friedrich sign in the jugular venous pulsation, where you have a high CVP, you have rapid early emptying, basically, of the atrium, and then a very quick plateau in pressure because the ventricle quickly reaches its maximal elastance or minimal compliance. Because we also deal with intracardiac lines, I just wanted to make a quick point about the difference in the morphology between an RA and an LA pressure. In an RA line, the A wave is the dominant wave on your venous pressure tracing. In an LA line, the V wave is the dominant wave. And there are two reasons that are posited for this difference. One is that the left atrium is less compliant than the right. The other is that the effect of respiratory movement is to create basically a compressive effect on the pulmonary veins that causes pulsatile return to the left atrium, or phasic return in a way that accentuates this poorer compliance of the left atrium. I mention this because if anyone ever comes back to the ICU, or the cardiac ICU, with a left atrial line, it means that there's concern for left atrial hypertension. And what you don't want to see as that patient has their sedation lightened and their muscle relaxant lifted is something like this, where you get a profound spike in the V wave associated with poorly compliant left atrium that's inadequate under those circumstances, and flash pulmonary edema. Okay, super. And then maybe just kind of the last big category of pressure monitoring is arterial pressure monitoring. And in order to explain how to think about the arterial waveform, it's necessary to introduce the concept of the Wind-Kessel effect. The large arterial vessels are what are known as Wind-Kessel vessels. They have a lot of elastic fibers, which allow them to act as capacitors. When the heart squeezes, because of the resistance in the peripheral arterioles, the large arteries fill more rapidly than they can empty. And so they distend and become capacitors during systole. So you basically have this occur. And the reason that that's very important is that when the aortic valve closes and diastole rebound in the large arterial vessels, pressurizes the arterial tree throughout diastole. It's the way that you maintain a diastolic pressure. This is known as the Wind-Kessel effect, and vessels that are able to do this are known as Wind-Kessel vessels. So when I mentioned earlier that we don't transduce PICCs because they're compliant, that's problematic because of this Wind-Kessel effect. And what that creates is the characteristic arterial pressure waveform. So I wanted to make just as a quick detour, a point about the difference between what we call the dichrotic notch and what that actually represents, and what's called an incisura. So people, what is the dichrotic notch? Does anyone know? Aortic valve. So that's actually classically what's talked about, but it's dependent upon where your pressure monitoring line is. If your pressure monitoring line is in the ascending aorta, then this little notch in what's called the dichrotic or descending limb of the arterial waveform is closure of the aortic valve. But anywhere else in the arterial tree, you're measuring a dichrotic notch, which is actually a more complex phenomenon. It represents reflected waves from the peripheral higher resistance arterioles. And I'll talk about that a little bit more in the next slide. But what you can derive from the arterial waveform is a systolic blood pressure, a diastolic blood pressure, and the area under the curve is the most accurate measure of the mean blood pressure. And that would explain why if your arterial waveform looks like this, rather than this, you can have the same systolic blood pressure, but a very different mean blood pressure, because you have a different area under the curve. But explaining what I meant by reflected waves is this is actually what creates the dicrotic notch in the majority of arterial vessels. You have a forward-flowing systolic pulse wave that distends the arterial vessels. Because of that Wynn-Kessel effect, about 50% of the blood that's ejected from your ventricle is stored in your large elastic vessels. The other 50% quickly makes its way out to perfuse the organs and tissues. It encounters the higher resistance arterioles, creating a reflected wave, kind of like dropping a stone in a pond causes ripples. That reflected wave moves back towards the central vessels and causes this secondary sine wave that can be measured in the circulation. And it's the summation of those two waves that creates the dicrotic notch when you are out of the ascending aorta. And this is helpful to remember because the position of the dicrotic notch in the dicrotic or descending limb gives you information about the dynamic of the circulation. So in a patient, for instance, with sepsis, who comes in with a very wide pulse pressure, one of the reasons for that wide pulse pressure is that there's pathologic dilation or vasodilation of the arterial tree, and that reflected wave either comes back very late or never, meaning that what's called the dicrotic notch is going to move way down the dicrotic limb and in some cases be invisible. And you see that upstroke and sharp downstroke. Because the area under the curve is minimal, you have a low mean blood pressure and a very low diastolic pressure. Similarly, if you put that same patient, or this same patient, on a vasoconstricting agent, what you do is you'd accentuate when that pressure wave returns to the central vessels. And you can begin to get fusion phenomena, sort of constructive interference between these two wavefronts, which causes the pulse wave to go up. So you see the dicrotic notch climbing back up the dicrotic limb. In patients with pathologic arterial stiffness, people like the Williams patients that we take care of, this phenomena can lead to an actual anacrotic notch, which is this little divot you see on the anacrotic or upstroke limb of the arterial pressure tracing, where the two waves occur simultaneously enough that you get constructive interference on this systolic accentuation, it's called, of the arterial waveform. Now, separate from looking at the arterial waveform and trying to understand what it's telling you about the state of the peripheral arterial vasculature, it's important to understand the characteristic arterial waveform artifacts. All transduction systems, pressure transduction systems, have a characteristic resonance, which is typically 200 to 300 times higher than the resonance of the waveform that the system is measuring. The arterial waveform only has a frequency of about 1 to 2.5 hertz, and most arterial transducer setups will have basically characteristic resonances in the range of 200 to 300 hertz. If there's a problem with dampening of the system, though, you can have natural resonance of the vascular tree cause basically a resonance close enough to the natural resonance of the transduction system that you get this underdamped arterial tracing. People call this ring or fling on the arterial line, and the importance of recognizing this artifact is that you will overestimate the systolic blood pressure and underestimate the diastolic blood pressure if you have an underdamped arterial line. Conversely, if you have clot or kink or an air bubble in the line, you get this overdamped tracing. In an overdamped tracing, you underestimate the systolic, you overestimate the diastolic blood pressure. So separate from consuming the arterial waveform and understanding what it might be telling you about the state of the vasculature, it's important to look out for these characteristic artifacts. And then the last point that I wanted to make is this reflected pressure wave that I was talking about leads in a healthy circulation to what's known as distal systolic pulse amplification. If you put a catheter in the aorta, in the femoral artery, and in the dorsalis pedis in the same patient, you would see this migration in the morphology of the arterial waveform. And that's because of basically the reflected wave arriving and accentuating the forward-moving systolic pressure wave as you move further out into the arterial vasculature and are more and more subject to the effect of the small constricting vessels. The last phenomena related to the arterial line that I wanted to mention was the assessment of volume responsiveness. And we talk a lot about how and why the CVP alone is not a good measure of a patient's volume status. If the patient has a restrictive physiology, you might have a very high CVP, and that might be appropriate and necessary to adequately preload that ventricle and maintain a stable circulation. The indexes that are available to us at the bedside obviously go beyond this, but this is probably the most accurate single intravascular pressure tracing to assess where a patient is on the Frank-Starling relationship, the systolic or pulse pressure variation, and you can get the Philips monitor to calculate this for you. It's basically the difference between the Pmax and the Pmin, and if that's greater than 10 millimeters of mercury, that usually suggests you're on the upslope of the Starling relationship, and you should try some intravascular volume if you're worried about the hemodynamics. If you think that the patient's very fragile, there are other things that you can do. You can do an expiratory hold maneuver if the patient's on positive pressure ventilation to see if that augments cardiac output. You can do straight leg raising. There are ways of pushing a little bit on the liver. There are ways of doing this without necessarily providing an external bolus. But recognize this phenomena and understand what it means. And then I'm just going to end by quickly talking about the future. The point that I was trying to make in this presentation is that the waveform data, in particular, that we gather at the bedside is extraordinarily rich as a source of information about how the circulation is working. And that's one of the reasons why the critical care data program is focused on waveform capture, using techniques like signal analysis, techniques like machine learning that allow you to automate the labeling of changes, for instance, in the morphology of these waveforms. We think that we will be able to discover a great deal more about the circulation than current tools allow. Because T3 is part of the monitoring strategy in our unit, also wanted to mention T3. The utility of having a display platform is the ability to look at these parameters in relationship to one another. And so you've all probably at some point looked back to try to figure out what CVP was associated with optimal cardiac output, the narrowest AVO2 difference, the best blood pressure. It's also useful to look at this as patients recover. After cardiac surgery, when the heart is stiff, you require a higher CVP to maintain whatever given cardiac output you've determined is adequate. As the heart remodels in that first postoperative night, you'll be able to maintain the same cardiac output at a lower central venous pressure. That's an important index of myocardial recovery that it's easier to discover utilizing a technique where you can visualize things on the same axis. And as part of this platform, the beginning of the introduction of these integrative indexes, like IDO2 that you see at the top of the screen here. IDO2 uses 13 different domains of patient data to probabilistically calculate at 5-second intervals the likelihood of a state of inadequate systemic oxygen delivery existing. And it's important to understand that what that specifically is pointing at is the instantaneous likelihood of a mixed venous saturation being 40 or less. I say that because in patients who have a mixed venous saturation of 40 on their best day, based upon where their arterial saturation is, this may or may not be something that helps you. And that's all I have. Thank you for your time.
Fantastic talk, very informative. The last Wednesday I was at cardiology research rounds, and there's a fellow who has a thermograph, and which is this camera that attaches to your cell phone and takes a picture, a thermal signature of whatever it's looking at, and it can actually look. It actually theoretically replicate what we do at the bedside, you know, in terms of touching pills, etc. Do you think at some point when you guys manage to integrate all these waveforms, which a computer will be able to integrate way better and way more accurate than we can at the bedside, and when there's technology to replace even the simplest things that we do you think that will be replaceable?
You've given talks on artificial
intelligence. Yeah, no, I don't actually, because I think that this is the distinction between a task and a role. I say that because I think that some doctors will be replaceable. So I think all joking aside, I think radiologists, pathologists, non-invasive electrophysiologists, I think that those doctors will be replaceable. A role goes well beyond the task of interpreting what the data might indicate about the patient's pathology. It also includes figuring out how to integrate that information into a treatment plan and how to talk to the family or the patient about what it might mean and make the right decision. And that'll remain the responsibility of the clinicians, the nurses, and the physicians at the bedside. We'll get better at what we do. I think that the medicine that you describe will be more than the sum of its parts and substantially superior to the medicine that we practice now. Much more certainty, much less indecision, but will still be necessary.
Yes,
Yeah.
I have a question for you. I was thinking about the future as well, and because we are getting better at getting data from the monitor, do you think we can get the dichrotic notch out and see where it is in the...
Yeah, there's absolutely no reason why. I mean, that's a signal analysis problem. You know, the EKG literature on this is actually it's very interesting. Our group took part in a PhysioNet challenge, and it involved interpreting, trying to make a determination about a rhythm class from a single lead EKG. The technique that Sebastian Goodfellow in our group used was essentially kind of a supervised technique where he hand-selected features. And we talked about this as a group for probably about 2.5 months and ended up with 300 features of the EKG that we thought helped us discriminate between these rhythm classes. And we're quite pleased with ourselves. There was a group in the same challenge that utilized a technique called deep learning, where the computer was able to select its own features utilizing a deep neural network. And that group had selected 2,410,000 different features from the same waveforms. And so I think that it's a situation where looking for the dichrotic notch is making available knowledge we already have. It's kind of reifying what we already know. I suspect that when you get into techniques that have the ability to look at the signal at much, much higher resolution than, say, the human eye, or think in many more dimensions than the human mind, we'll be able to select many, many more features from the arterial waveform that'll inform us about the hemodynamic state of the patient than current methodologies allow.
It's not the same when the systolic pressure is 90 or 100 rather than the systolic pressure is 50 or 60. But I say that 10 millimeters is easier to see in bigger patients than in smaller. So somehow the pulse pressure variation is not as easy to see.
In smaller patients, that's right. You're saying with the lower blood pressure. Yeah, absolutely. I would advocate that you become familiar with the pattern. And if you believe that the oscillation of the arterial pattern suggests basically greater variation than you would expect, you think about that as an indication to try to investigate where the patient is on the Frank-Starling relationship. Possibly by smaller measures than a full bolus if you're concerned about the patient, but just recognize the pattern. Okay? Super.
Thank you very
much. Cheers. Thank you. Yeah.
So this is the key to life, aerobic metabolism. It's how we get enough oxygen to the cell to produce about 30 ATP molecules per molecule of glucose. That's what keeps us going, what keeps us active. And as derived from the amoeba, this is probably, in my mind, the most critical measurement in physiology that we can't measure, and it's the Pasteur point. It's the minimum amount of oxygen required in the mitochondria to allow for oxidative phosphorylation. Right? So all the oxygen cascade and the delivery is all to get to the mitochondria so we can use that oxygen to generate that ATP. In the amoeba, it's about 1 to 3 millimeters of mercury. Not very much at all. Don't know what it is in a human. I hope at some point we can have a little probe somewhere and it will tell us what it will be. But it's a reflection of just how much oxygen reserve we generally have. And this is what we do to deliver that oxygen. We think most of the time in the right upper quadrant here, which is the heart. But it's obviously got to get through a capillary bed, of which there's some interstitial fluid accumulation and filtration that's drained back via the lymphatic system. And we can also look at and calculate the balance of oxygen delivery with demand. And that's really the key management practice in the ICU in my mind. We can sometimes calculate the oxygen delivery by the cardiac output and the content of oxygen in the arterial system. We can look at utilization, the demand of oxygen by oxygen content coming back to the heart and the cardiac output. Measure cardiac output, we can do these calculations. But we need to have targeted sampling to be able to do that. And most times, we don't have this at all. Most times, we're making a judgment call at the bedside as to what's going on. And we're using the signals that Jai just talked about. His talk was really important. If we don't understand the generation of those signals and the artifacts that can occur within them, then we will be basing our decisions on erroneous data. Well, because it's a cardiac unit, let's start with the heart. And perhaps the definition of low cardiac output, insufficient blood flow pumped by the heart to meet regional oxygen demand. It's pretty straightforward. The important thing here is the heart's just a muscle. I don't want to put it down at all, but it is. That's all it is. It's good muscle, you know. It's cardiomyocytes that pull on each other, complex calcium handling, etc. But it's really the complex interaction between the myocardium and the endothelium that determines this balance between supply and demand. And within that are complex interactions with neurohumoral factors, sympathetic nervous system, and autoregulation. So while we tend to think about the heart and we focus on it and optimizing its performance, we have to think about how it functions within the overall system. And one of the problems is, how do we define low cardiac output? Well, first of all, the big mistake I think we make is we call it, it's generally referred to as a syndrome. It's not a syndrome. Hyperplastic left heart is a syndrome. Downs is a syndrome. This is a complex physiologic state that is dynamic and variable. It's a state, not a syndrome. But there have been numerous attempts to try and define it, and these were summarized nicely by Brigitte Stiller when she looked at prophylactic milrinone prevention of low output. I'm not going to talk about milrinone other than to say it made no difference in this particular set of studies. But these were the definitions that have been used in the literature to describe low cardiac output state in children. Lactate, central venous oxygen saturation, arterial to central venous oxygen saturation difference, urine output, skin temperature, and then cardiac index as determined by Doppler. These are commonly used and commonly cited in various articles. Each one of them is not getting at the true measurement that we can have at the bedside. And it's interesting that they're a combination of the things that Jai was just talking about. And it's not new. Back in 1959, so the early years of cardiopulmonary bypass, particularly early years in tetralogy repair in children, the group from Hopkins described what they called sudden death syndrome, where they described in infants a fall in mixed venous saturation that occurred some hours before a measured fall in cardiac output, and then death. They didn't have the drugs to manage it at that point in time, but it was a well-described phenomenon. And then back in 1975, Kirkland and his group also described the low cardiac output, and the lower the cardiac output, the higher the risk of mortality in children and infants who had undergone cardiopulmonary bypass. Not new. This is perhaps the first study that really tried to objectively measure it in a single cohort of patients, and this is the Boston circulatory arrest study. I was involved in the tail end of this study. We had, out of 175 or so patients, 122 that we had accurate measurements of cardiac output via thermodilution. And what was detected was that within some time, usually within the first 6 to up to 18 hours after surgery, there was a decrease in cardiac index measured by thermodilution of 20%, associated with a high SVR and a high PVR. But notice it's very time limited, and really within 24 hours that started to improve and to change. perhaps not surprising, because the contributing factors were, well, the surgeons had induced some trauma. There was an inflammatory response, and there may have been myocardial protection issues as well. And this is the generalized systemic inflammatory response to bypass, where you have blood that is now seeing non-epithelialized or endothelialized surfaces, results in release of inflammatory mediators with this adhesion molecule cascade, transmigration across injured endothelium, a respiratory burst, release of oxygen-free radicals and tissue injury, and a humoral response via complement, icosanoid, and fibrinolysis. That's pretty well characterized now. And then on top of this is increasing evidence of really the effect of cellular and molecular mechanisms after pediatric cardiac surgery related to the immaturity of the mitochondria itself, but also the reperfusion injury and how we can mitigate that. And Georgia's involved with a group in Melbourne and part of a multi-center study that will really start to target this type of effect by potentially ameliorating it with something like nitric oxide. But this was the population of patients we had back in 1990. This is transposition, comes back, edematous. And it's important to understand, though, that we had large priming volumes in our circuits of nearly 800 cc to a liter. We cooled them rapidly, warmed them rapidly, had a low hematocrit, and we used an alpha-stat blood gas management. So it was completely different to what we do now. So is there an era effect? Well, over the next number of years, we did a whole series of studies looking at different things like the pH management during hypothermia or bypass. Siloxane we used as a blocker of the adhesion molecule cascade. It had no impact, interestingly. High hematocrit strategy and the use of thyroid hormone. So we had these number of patients over these next set of eras, and interestingly, in the same population of patients, there was still this fall in cardiac output seen regardless of what we thought were improvements in the technique of bypass. We were still seeing this decrease at around sometimes 6 to 18 hours. Also of interest, though, the index stayed relatively normal. The lowest index was still just 2.5 to 3, as opposed to around 2, which it was in that first study. So perhaps less injury in the myocardium, less inflammatory response, but you still saw that. The reason I mention that is that part of the management of our patients with low output state is anticipation. We are too reactive. We wait until the temperature cools off. We wait until the pulse width narrows, and then we're trying to decide on what the management strategy is. There is very good evidence that we should be anticipating it and ahead of it to start with. Even if you don't have a subjective clinical sign, don't wait for the clinical sign. It's often the last sign. And there is additional data that's coming out about the more contemporary data, I should say, from 2016. This is a group from 2 centers, Ann Arbor and in CHOP, and they really wanted to look at complications and mortality, failure to rescue, and how they responded to complications, either prevention, recognition, or intervention. That's okay. 2 centers over 5 years, 191 infants, 80% of them, 87% were newborns. And once again, they could not come up with a definition for low cardiac output state. They couldn't measure it, so it was by consensus, which really bothers me. We shouldn't, anyway, it is by consensus. So they found, not surprisingly, that if you, by consensus, had low cardiac output, 71% of those children at any time had it. And in 38%, it was the seminal event that occurred. So low output state should be anticipated. You should be prepared for it, and ahead of in terms of the management. The problem is, as I've said, is how to define it. Clinical examination, and Jai made the point that we have to examine our patients. I agree completely. Problem is, there's poor relationship between studies that have looked at clinical exam and objective measures of measured cardiac output. We tend to overestimate cardiac output and underestimate SVR. And a number of studies have shown that. So clinical exam doesn't necessarily help you. It is important to do. Routinely monitored physiologic signals by themselves, also problematic. Blood pressure, very poor relationship, other than newborn hypertensive post-bypass. Coming back to you in the ICU, be very aware of those patients and get that blood pressure down because the myocardium is under a lot of stress and can potentially fail very rapidly. Heart rate, weak correlation. NIRS may be useful, but as a trend monitor only. Arterial end tidal CO2 may indicate pulmonary blood flow, but in terms of being able to tell you what's going on with cardiac output, no. And other measures, other indices that we can measure, once again, poor relationship with cardiac output. Biomarkers, lactate, yes, but it's a late signal. And often we'll be, we get called to the bedside, the lactate's gone from 1.5 to 2.5. It's really not much of a change. If it's gone from 1.5 to 4.5 and then 7.5, that's the change that we look for, and that's the change that's associated with low output and risk. But mixed venous sat still remains the best marker, and that's why we use it as the best surrogate we have for cardiac output. The problem is it's intermittent sampling. There are catheters that are available for continuous monitoring, but they're fairly stiff. They can stay in for up to 24, perhaps 48 hours, but we don't have the ability to continuously monitor, yet it's the best index that we would have. And these other measurements, thermodilution, Doppler bioimpedance, pulse wave contour analysis, and FIC, all have their limitations. Point is, it's very hard for you to objectively measure cardiac output at the bedside. And yet, if we look at the equations for what's determining blood pressure, which is one of the things we respond to most, preload, contractility, afterload, all determine myocardial fiber shortening, and along with ventricular size, determine the stroke volume. Stroke volume and the heart rate then determine your cardiac output. Your cardiac output and peripheral resistance determine your blood pressure. Fairly straightforward, well documented, well known. Blood pressure is a downstream surrogate for all of these. And there are limitations in how we monitor, as Jai just pointed out. Heart rate, very important monitor for potential changes in cardiac output, clearly. But once again, it's important that we understand what the heart rate means within the context of the patient and look at that, the waveform as well. And then right down here we have preload with a dotted line around it because we tend to use CVP as our surrogate for right-sided preload, which is sometimes appropriate, often is not. My point is that to try and get to each of these important aspects of the circulation, we're using really quite indirect measurement. Now, one of the first things we did when we started to collect continuous data was we wanted to look at what was the range of normal for our children. Currently, the normative range is based on healthy ambulatory children. None of them apply to us in the ICU. I asked nursing staff how they set their ranges of normal on the monitor. And you can do it by the Phillips normative range. Others set it based on a wide range, based on what they thought that should be in the discussion at the bedside. Others set it based on quite a narrow range, particularly if they were doubling on a patient so that they had a narrow window, the alarm would go off so they could respond. But we set out to try to understand what the range of normal might be. So these were centile curves that Danny Ayton generated from well over 1 million data points. This is for all children admitted to our intensive care unit, right? So this is just age. And we could generate a whole family of centile curves here. This is from the 5th centile up to the 95th, 97th. And you can see that there is this range here. You can see the breadth of that range. Doesn't necessarily help you, so we then said, well, let's look at various subpopulations. So Danny then, this is 19 different admission diagnoses and time course, and was able to, both PQ and cardiac, work out where those population of patients sat in terms of their range of normal. Still quite broad, we have not translated that to the bedside yet. Because I think the most important data that came out of this, in my mind, from Danny's work, is that, yes, we can have this range, this is heart rate, this is systolic blood pressure, and you can have this mean and 25th, 75th centiles of the range for the pressure or heart rate for that population of patients. But within that population, each patient had a much tighter rein for their blood pressure or heart rate. So they tended to have a narrower, within about 20% of their blood pressure. So you have a wide range for a population, but each patient within that is much tighter. And that's what we do. We maintain our homeostasis quite differently, and I'm sure I'm going to be different to Jai and certainly to Alex, you know, a fit young guy. So it's going to be important that as we move forward that we start to understand what the phenotype of our patients are and personalize our management. Now, a lot of our management is based on the Frank-Starling law of the heart. Otto Frank studied isolated frog hearts in around 1908. He also described the Windkessel effect, as it turns out. Starling worked separately in the UK at around 1910, 1912, so over 100 years ago. He used a lung heart prep in anesthetized dogs, and they both described this Frank-Starling law of the heart where end diastolic fiber length and stroke volume are related. And so within physiologic limits, the force of contraction is directly proportional to the initial length of the muscle fiber. So about muscle fiber length, how much that is stretched. And over time, it's really that physiology has evolved to understand the ventricular vascular couplings, interactions, and cardiorespiratory interactions. And this is really an extension of the work by Starling and Frank, where they're looking at the effect of preload and volume on cardiac output. And this is more so in the last 50 years where the effect of afterload and arterial elastance has played an impact. I'm not going to go through each of these other to say that this whole understanding has continued to evolve to the point where we know that there are significant ventricular arterial interactions within the heart. And this is the normal heart works at peak energy efficiency. So your contractility, that intrinsic ability of the heart to squeeze, overlaps or exceeds the afterload stress against which it is ejecting. Compensated heart failure works at peak efficiency and contractility now matches afterload. And in this particular situation where there's heart failure, contractility can't match afterload. Important point here is that we're now starting to see that it's not the heart, it's the heart's muscle, its intrinsic contractility is an important component, but it's the load under which it works that is really important. And the most important organ in the body is this one. It's the vascular endothelium. It lines the entire circulatory system. Heart, veins, arteries, lymphatics. It's responsible for regulating oxygen delivery, fluid filtration, vascular tone, hemostasis, hormone trafficking, inflammatory responses. And it comes in different varieties. Within our major blood vessels, it consists of endothelial layer with an intact basement membrane, some intercellular clefts, but it does not leak. Come down to the capillaries and we start to see fenestrations appearing within the basement membrane that allows that transudation of fluid into the interstitial space and the transfer of oxygen. And it's under control of some pretty important systems that we impact. Centrally, under the neuroimmune, some sort of neurohumoral communication through CNS activation and the hypothalamic pituitary adrenal axis. At a cellular level, through coupling of G proteins, and that's where the receptor active regulation comes in, adrenergic, vasopressin, and angiotensin, and really the release of calcium, intracellular calcium, modifying and controlling smooth muscle contraction within the endothelium. And then intracellular is where the alteration in second messenger pathways occur, and in particular the expression of endothelial nitric oxide synthase, which results in cyclic GMP-mediated vasodilation. And much more is now understood about that expression through the release of mitogen activated protein kinase genes. Point is that it's a very complex system. It determines so much of how our not only organs function regionally, but it determines how we will deliver oxygen. You can pump as much as you like. It's what's going on downstream that's going to be most important for you. Problem is, it's very hard for us to manipulate the endothelium. And then the third component to that are the lymphatics, often the forgotten circulation. They're lined by endothelium. They have a narrow, a small amount of smooth muscle, but they've got a fenestrated and incomplete basement membrane that allows fluid from the interstitial space to diffuse within them. And that's a very important component because Starling described another force, and that was the fluid movement across capillary membranes. And that's dependent on the driving pressure at the arteriole end of the capillary and the balance between that driving pressure out and the interstitial pressure that would be preventing that, and the balance between oncotic pressure between both interstitial and vascular spaces. Important point here is this R, this permeability coefficient. It's a glycocalyx full of glycoproteins and glycolipid. That's what regulates leukocyte and platelet adherence. That's the barrier to permeability, and that's what gets disrupted in inflammation and in our patients such as cardiopulmonary bypass. It's extremely hard to manage and manipulate that. Once we start to see that disruption, we don't have a drug that's actually going to reverse that injury. The lung, of course, is really quite different. The lung, of course, has now got a subatmospheric interstitial space, if you like. This is the capillary here, red blood cell. This is the alveolus here, interstitial space. And because you've got a subatmospheric pressure, there's a greater driving pressure of fluid, net fluid, out into the interstitial space. We produce a lot of fluid in our lungs. Being able to drain that fluid is absolutely critical. And therefore, I'm going to make one plug about the positive pressure ventilation and PEEP. We don't ventilate according to the ARDSNet strategy about trying to reduce lung injury, and I don't understand why we do that in patients with healthy lungs, let alone those with heart failure. Positive pressure ventilation has an impact on the systemic ventricle by reducing wall stress. But it redistributes interstitial fluid into perihilar regions. Both those factors are critical. And when you're ventilating a patient with heart failure or a low output state, just remember that you're trying to ventilate the heart as much as you're trying to ventilate the lung. Let's get back to our previous picture here. So we know that there are various loading conditions on the myocardium from preload, contractile, afterload. And I haven't talked about the maturational differences in the myocardium. We actually don't know a lot about the maturational differences in the endothelium of a newborn. You had the endothelial injury that occurs with inflammation, the tissue injury with leak, and now you start to see major problems with on this system that then results in an imbalance of the supply and demand. So there are some ways in which we can treat this. I'm sorry, this is coming up before I wished it to, so I'll push another button. We obviously address cardiac output, yes, with volume, but not too much. Make sure we've got some sort of synchronized rhythm, inotropy, and the way in which we ventilate the heart. I'm not going to talk about drugs. There's great variability in what is used between centers, and there has not been conclusive work done in our patients as to what is the best line of drugs, the best type of combination of drugs that should be used. So the other is how do we decrease the leak of fluid across these, the endothelium, and in particular the way in which we fluid manage. He showed that edema of the child back 20 years ago. Our major therapy at that time was to give volume. There's been a major shift in the last 20 years away from that, and particularly I think in the last decade, So yes, we give volume, we need to maintain the circulating volume, but more likely to use a vasopressor. When I was training, if we used epinephrine or norepinephrine, it was certain to induce coronary artery spasm in the cardiac surgeon and a tirade of all sorts of things. Our focus is on supporting organ function. I talked about ventilation, but the other is that to minimize oxygen demand. And that's where it comes into understanding what are the modifiable contributions to a low output state. We have the residual loading conditions from surgery, but there are things we do that can potentially make this worse. First of all, we don't minimize oxygen demand enough. We have a patient who's got an open chest, low output state, who's not paralyzed, moving around, consuming oxygen. Temperature control, which I talked about how important that is. Being cautious with volume replacement. More volume you give, the more that goes in interstitial space, the harder it's going to be to get that fluid out. Mechanical ventilation strategies I mentioned. And there is this variability in inotrope and vasoactive support, and I really don't advocate for one or the other than understanding what you're trying to do with that drug in terms of both supporting the myocardial function as well as whether you're wanting vasoconstriction or dilation. So low cardiac output is really about appreciating the complex interactions and targeting management accordingly and understanding that's variable. We all have a different phenotype, understanding the risk, and then starting to characterize the features of the physiologic signals as Jai talked about so we can track our response to therapy. And this is what we've been doing for the last few years here, is trying to do some complex and in-depth analysis of continuous physiologic data. And I certainly believe that this is where we're heading. Machine learning is going to make this a completely different field for us in the years to come. And it starts with collecting all the data and storing it permanently. That means you need a data management platform that can handle that, and Bobby and Andrew and the team have developed that. We want to see and interact with the data, and that's where we have a risk-based monitoring like T3. And then we need to understand that physiologic state of the patient and what the risk for an event is within that state. Too often we're trying to anticipate what the event is. You've got to go back a step and say, what's that physiologic state? And within that state, what's the risk for the event? And it has to be available at the bedside, so you guys can make real-time clinical decisions. And of course, it has to be there for research as well. Jai, some of the work we're doing, Jai talked about the atrial fibrillation classification using step-by-step machine learning. This is something that Sebastian put together. This is the percent normal sinus rhythm or atrial fibrillation in this continuous waveform. That sort of machine learning is going to be available real-time at the bedside so that you'll be characterizing, rather than you having to make the decision, you're going to have the algorithm making that for you. We collect a huge amount of data on all these signals of very high frequency. And Danny's working at trying to characterize cardiopulmonary interactions. And in this circumstance, if we take this gap in time there, you can see all the overlap of waveforms, and we keep going deeper and deeper into that waveforms. We can start to see overlap of end-tidal CO2, blood pressure, and systolic trace. And if you keep analyzing and going deeper into this data, and you'll start to see, as Jai calls, more subtle phenomena, the hidden variables, which in this case are Herring-Traub-Meyer waves, which are an indication of sympathetic activity or autonomic and autoregulation. This type of data is not available to you at the bedside, but it is available through this type of machine learning, and it's going to make it so much different for us in terms of understanding what we're dealing with within that circulation from cardiac and endothelial interactions. What we've done with T3 is, with the inadequate oxygen delivery index, is to take looking at the probability of an evolving state. And I won't go through these in much detail other than say that patients initially from Boston Children's, we did what we call a full data set, medium and a minimum data set, and it gets displayed here on the T3 platform, and these are the variables that go into making that model. And then you do your various operator curves, and you can see that based on either the full, medium, or minimum data set, that there is error under the curves around 0.8. And this gets to your point, Alex, as to how you can believe the data, how you can trust the data. And you're not going to be replaceable for some time, because what the data is doing is trying to give you an understanding of what's the probability of something about to occur. This is not automated machine learning. This is not an absolute, yep, that's cardiac output is 2.2, and this is what you do. It's rather, you've got these area under the curves that are acceptable, but they're really an indicator. They're not, they don't tell you exactly what you need to do. It's another tool for you to interact, and it's integrating a lot of information together. And as long as that's the case, you'll still be needed at the bedside. So I wanted to finish with this last one. I'm sorry, because I think this is the future as well. And this is where we start to integrate data from a whole lot of different sources. And these are just ECG, saturation, and blood pressure. But what we're seeing here is the relationship continuously between those signals and then some perturbation in those signals. We're going to see a much different way in which we understand the interaction between these signals. And once we understand those interactions, then it's going to be, I think, a much more powerful and persuasive argument as to how the cardiac output from the myocardial perspective and how the endothelium are working together to interact that most important thing that we need, oxygen, and how we deliver it. Thanks for your time. Of course you can follow up, Alex.
Since I'm still needed. So the challenge I have at the bedside is that, as you mentioned, most of what we worry about is the coupling of what we deliver versus what we need, or what the pump can supply versus the state of the vascular system to receive it. What good measures do we have, and sort of building on Jai's talk in terms of what we monitor? How can we monitor the vascular entity in terms of the
vascular tone?
The vascular tone, particularly in the setting where we have myocardial dysfunction or potentially even myocardial failure following pump.
Well, we could be measuring oxygen VO2 continuously, and have properly placed central venous catheters for doing intermittent measurements of SVO2, correlate that with a real NIRS, i.e. one that is actually accurate, like the one we get from the Nona, not from the other. So you get a trend, and you understand how those NIRS and the mixed venous work together. The reason you do that is then you have a NIRS that you can measure longitudinally and follow, and you have VO2 that's being measured continuously, and now you can start to, in the real time, calculate what your, by a FIC, admittedly with some assumptions, what your cardiac output is, and then work backwards and understand some idea of resistance. I think that's something we could do quite readily and easily, but without doing anything more complicated than what we have at the bedside right now. That would be one. It's very hard to get a continuous measure of either interstitial fluid through bioimpedance or through vascular tone using cuff methods and others. It's just not a continuous sample. And that's what we need, is something that's going to be a continuous sample. I think pulse width, diastolic pressure, all of those are important indices and markers. And as we, instead of looking at them as isolated numbers, but as we start to put them into the type of deep learning that Jai's talking about, we'll start to see what are the important numbers, how they vary, and what they will actually indicate in terms of the therapy we give, the response to that therapy, and how we modify it. Okay, thank you very much.